ఇప్పుడే స్టార్ట్ అయింది.
If you ask me to come forward, because I'm going to come hard stuff. Okay. Yeah.
Very good morning to everyone. I am Manisha. I welcome you to the day 3 of National Training Workshop on Weather Radar. Before we start the technical session, I would like to inform that the IIT of Pune is organizing WMO conference on weather modification on 3 to 7 November 2025. The deadline to submit an abstract is 11th April 2025. So abstract submission is free. All are encouraged to apply for this conference. So I would like to call upon stage Professor V. Chandra to say a few words.
Yeah, sir. He doesn't think I know how to put it in my pocket. He has to do it. Okay. Can you hear me? Good. I'll be paying attention to you. Yogesh will refuse to move forward. And can you hear me? You know, today's main topic is radar network, and then it will transition to a lot of operational things that Roberto will talk about. Roberto, can you stand up and turn around? He's going to talk today about that. But before that, I wanted to tell you the whole concept of radar network has changed. And, you know, in the old days, everybody had even weather service radar or even IMD, everybody had uniform radar, same kind. You know why? It is not related to science, because that's what the finance people said. You will buy only one type of radar. We don't know how to evaluate multiple radars. Unfortunately, we have been suffering under those things until now. And but that doesn't mean you can suppress how business is done in real world. That's problem number one. Finally, you can see IMD itself has changed now. They are buying multiple frequency radars and other things. First thing. And otherwise, what they will do is they will buy a big S-band radar and put it in a small valley in Northeast, because the finance people said that's all you can do. You cannot buy it, right? That's a real life. I know you don't want that big because you don't want to be in trouble. Second thing is, take this is more serious, because this is a problem that Renzo and I deal with every day. What happened to Luca? Oh, you scared me. I was like, what happened? So, this is in Mumbai. Rajashekar. Rajashekar? Oh, no, Rao. I knew something was wrong. Whatever I say, you keep correcting me. I was like, sorry. I'm sorry. So he will put out rainfall on Mumbai, because that's his job, right? Whereas Subrata and his crew, Deshpande, they will put rainfall because they like to write papers. And then there will be some common place, and these two rainfalls will be different. Each of them will say my rainfall is the best. Then some third guy will bring some gauge from some hydrology department. Where is Elon? No, he will bring a totally wrong working rain gauge and he will say both of you are wrong because this gauge is correct. The reality is, in the olden days, agencies, there was no social media, nothing. Agencies were too strong and then, no, he is wrong. Then each one will say other is wrong and then Subrata will do one case study and show his rainfall compared very well with the gauge. And then I'm good. Whereas Rashekar has to do it every day, not for one case study. And then he will produce, and Elon will continue making wrong rain gauge measurements. But that type of life cannot go on anymore. And we are all being forced to merge the two things. It's like what I call as mainly because too many people in the public know about this. And then there is some guy will from internet will come, they will take your data and say, I'm giving my own forecast. You don't need all these people, right? That's also there. So this is sometimes a curse as well as an advantage. So we are ourselves forced to, so you have a clock tower, okay? Clock tower has a clock one, and then you look at it, it's good. But if you have a clock on four sides, this is called a clock tower problem. Your first job is to show all four clocks show the same time. Otherwise, even somebody who doesn't even know what clock is, I can't, you spend so much money, what is this? How each clock is showing different time. Everybody will criticize. So, this whole concept of merging radars from X band and S band, C band appropriately, and then at the same time being cognizant of what is being seen with the rain gauge, it has become a collective responsibility. So we spend so much time doing this in California now. We have X-ray data, we have our own X-band network, we have our own C-band radar. Then finally we put all that and then do first thing is we do history. So that we have to make a composite reflectivity. But secretary the other day said that we should have a national mosaic. And he doesn't know detail about radars, but even he knows there should be a mosaic. The mosaic will be he sees a jump between two radars, he will see it immediately. So these are problems that we have historically ignored and just stuck to our ground and correct, but they'll be in your face. We cannot ignore it anymore. So I suggest right now, you two guys make a friendship pact. Because your job is to produce rainfall, his job is to get rainfall and then publish paper. I don't think he's got a mandate to produce rainfall every day and want people and vacate people, right? You're a research institution. But we say that. And then it has happened to me, though I'm saying it as a joke, there was a very famous flood in Fort Collins in the year 1989 or 1999. Can you look up Google Fort Collins flood? And it rained 10 inches in 5 hours in our city. We are not even monsoon region. How much is 10 inches in? And you can figure it out. 250 millimeters, right? So, and that's a lot of rain even here. So in 5 hours. So there was a flash flooding and many people died, a train got flipped over and so many things happened. So after that, 1 year later, there was like a memorial conference and we had our radar. And then I got very good, very accurate rainfall rate compared to the weather service. So for me, I'm going to put in the shoe of Subrata. So I was showing, see how great it is. I got the rainfall, I nailed it. And weather service rainfall was underestimated. Somebody got up from the crowd. So this is 1999? No. 1997. 97? Okay. So which means this meeting was in 98. Many people are not born in 98. Anybody here not born in 98? Oh my God. Okay, so I get up and talk in the conference. I was expecting people to say, wow, you did great. You got the rainfall, right? Do you know what the response was? Can anybody guess? If you're so smart, why didn't you tell us? And he exactly used these words. If you think you're so smart, you got it right. But you realize I'm not in the business of issuing warnings and watches. So, but at the same time, you cannot say, that's not my job. And but we have a social responsibility to say something. So I think my first suggestion is, I don't know how it's going to work, but between Subrata and Rajshekhar, we make a pact. No matter what happens, we will fight internally, the fight won't go out. Because if the disagreement comes out, both of you will look bad outside. I'm just, making a lot of jokes, but there is a little bit of seriousness in this. So it will be important to come up with he's got a nice C-band radar. He doesn't have to work with the airport radar anymore, right? No, I don't want to say more. I don't want to get you in trouble. and so that has a lot of coverage. I think I can help. We have a lot of experience doing this. How to merge expand network with because it will be a small patch, this expand network compared to the big C-band area. How you can put the rainfall together. So radar networks like this, so many people will come with data. Very soon, many universities in Andhra and other places, they are starting to buy radars now. So people will come with radars, they will make their own measurements. So we need to have some sort of a protocol to bring together heterogeneous networks. Finance people, however much we complain, they made our life easy. They said you will buy only one type of radar. We didn't have to deal with all this heterogeneity. So now I'm talking positively about finance people. So you buy two different types of radars, they will be with two different systems. This is becoming extremely important. So today's topic, with this introduction, I hope all the young people in this audience, especially those who said who were not born in 1980, 97 or 98, that's your future. Because a lot of these processing techniques will have to be needed to put all the data together from multiple radars. With that introduction, I'm going to hand over the conference to people who will talk specific things. Any questions before Renzo pushes me out of the stage? Yeah.
Recently, we had a meeting with who also.
Oh, I know about that.
They make this multi-sensor, multi-radar network, and they were using all similar S-band radar. So
I will talk about that off.
So we were thinking that US put all one type of radar at one time. It was very, very nice, whereas we are augmenting different types of radars in different time domains.
I know what you're talking about. It's called MRMS. So it's a whole another discussion. So and my discussion is being sent by streaming and recording. So we will discuss honest discussion. Yeah.
Emerging technology.
Sorry?
MRMS is also emerging technology because it's widely.
I think you're trying to force me to say something about MRMS, but I will do it offline, okay?
Since we are here to discuss about the merging the product in a larger domain. So what are the ways to do that? So that's what Sir was telling is that is the one way to get into it. There may be other.
Let's forget about MRMS. MRMS, it's like I'm looking at how to wash clothes. Then you are specifically asking me about wash machine. Yeah, you are forcing me to make a statement, but let's step that aside. So we are discussing whether washing in the river or washing with a machine or some ultrasonic washing.
We are not forcing anything.
No, I understand, but what I'm saying is that what I am talking about is something different. It is half of it is technology, half of it is sociology.
Completely.
It is not, it's a technical problem, it will be solved by now. It is not a technical problem. It's a sociological problem. And 9 out of 10 times is to working and trying to get the information properly. And let me give you a very simple example. Okay. I'm just going to use you two as examples because you're friends and I'm making jokes, so you know I'm not serious. And let's say Subrata makes some measurements and then he wants to merge reflectivity data from the C-band radar in Day. Then he does his attenuation correction, you do the attenuation correction. The reflectivities don't match. But then let's say he finds out that, oh my God, our radar has been off by 3 dB all these years. He may not want to change it. And then you cannot make him change it. Then there are a few ways of doing this. You are in the business of making the merge data. I don't call it mosaic. Mosaic is different. Okay, if I know that the data is coming from that radar, I'm just going to add 3 dB and deal with it and go on. I'm not here to convince him we should change. But if I use his data, that's what I would do. There are a lot of this give and take, and then how you merge, which radar you use, where it is, and sometimes one radar has blockage somewhere. You don't even want to use that data. There's no point in making some blockage correction and then this and that. We deal with that every day. As per every storm is over. Last night I was in a call with Amira. I kept you out of the discussion about March 31st case. The products are overestimated. Were you talking about that? No, I don't think so.
No, I know. Yeah.
And so I was in a meeting last night. So we deal with this every day. So, and until you start engaging, I come at an overlapping level and tell people, hey, let's get together, solve the problem. That's very important. Otherwise, if you don't do that, everybody will look bad at the end of the day. And so, MRMS was a different thing. So it's not even in the topic. That's why it's like if IMD had its own radar, all S-band, and they had to come up with a national map, MRMS is something similar. And other questions? I'm telling you, a lot of these innovations will come outside the agency. Some student will come from outside and then, hey, can I do this? Can I do this? Can I take this data like this? And then you'll put it. First thing you will find is this formats will be different and people will spend 2 months just writing other people's format. I try to. So, Amen, does it sound familiar? Dealing with formats? So there is IMD radar, NIoT radar, and some other radar. Everything will come in its own way. You have to deal. Oh, more importantly, in the same area, we have 3 radars in our area. One radar will start here, another radar will be up here. They can't even start at the same time. And it's a 6-minute scan. So there's a lot of issues. So I don't even want to get into the details. Other questions? Otherwise, I'll sit here and too long. Give it to Denzel. Thanks.
Okay, so I will start. I will continue this discussion about network, starting with this presentation, and I will start from very basic concepts like network topology. this, I have a few slides at the beginning that are mainly based on the work of Francesco Nugent and Chandrasekhar, which was a work propedeutic to the first deployment of the CASA network in Oklahoma around 2009, 2010. So when talking about network, we have to think about the framework to relate the network coverage and characteristics to the individual radar characteristics. And with the aim to have some objective elements to evaluate whether a network can improve some of the characteristics of the high power single long range radar instead of a network of a smaller radar. So with this, start by defining some elementary concepts for the network topology. So in his paper, he actually considered several tiling geometries. So he considered triangular, square, and hexagonal, and ended up evaluating that the triangular mesh is the best one. So I will focus on this. So you see this minimal network depiction, including 3 radars and a single radar network. So this is what we call a radar network. This is the maximum range of the individual radar in the network, and this is the range of the cell, of the network cell. So then we define overlap ratio, M, as the ratio of the maximum range to the range of the cell, and an angular separation theta between the radar and the center. That for a triangular mesh is 30 degrees. You can see I have 2 examples here. One is M equal 1, the dashed lines. This is the minimum overlap ratio to cover the network cell. Because all the maximum range in this case intersect in the middle of the network cell. And M equal square root of 3 is a range, an overlap ratio that allows coverage of the same cell with at least with the 2 radars. So it provides redundancy. So these 2 values are the most interesting. So let's consider this network of 4 radars with the 2 network cells. So in this case, we have M equal 1. And you see, and every network is covered, but there is a very little overlap with the radars. And N equal square root of 3, which allows coverage of each network cell by completely covered by 2 radars. Okay, and if you look in the real world, I mean, this is very ideal. You know that in the real world, very often we can get close to such regular geometry, but indeed there are many examples that actually come close to these ideal deployment strategies. This is the CASA first deployment in Oklahoma. You see that they had 4 radars building up actually 2 network cells with a very similar geometry. Then if we start to put some number to this ideal figure, then we can also elaborate some number to compare different strategies. So let's say that we want to cover an area about 260 by 260 kilometers. With the radar, whose range is between 150 kilometers to have an overlap ratio of 1, and 260 kilometers to have an overlap ratio of square root of 3. So then we can introduce some characteristics of the network related to the characteristics of the individual radars. So the main, the relevant characteristics that we want to look at are the beam size, the average beam size over the network, so the beam spreading with distance, and of course, the lower the average beam size over the network, the better, the most accurate is will be our measurement, and the beam height, the minimum beam height over the network. So both parameters. Don't go into the detail of this equation, but basically the average beam size is related to the to the beam size of the individual radar at the maximum range, and the overlap ratio and the separation. So given these parameters of the network, one can calculate what is the average beam size over the network. And analogously, you can calculate what is the average minimum beam height over the network, starting from beam height at the maximum range of the individual radar. Then the other very important parameter that we've been talking about these days is the radar sensitivity. So we've seen this picture before. This is also called the noise equivalent reflectivity factor. You remember that we replaced the noise, the minimum detectable signal in the DBM, the radar equation, and we derived this line which represents the sensitivity of the radar. So this is for individual radar. Then we want to calculate the average sensitivity over the network. And this is done by introducing this equation where this Cmax is the radar sensitivity at the maximum range of the individual radar, which means this value here in the plot. So this is, of course, reduced by this factor to get the average over the network. And I'll let some concrete example to better understand this concept. So let's actually go to have some number. Let's consider first a C-band radar with a radius maximum range of 150 kilometers. Here we have our beam with the beam width in red. This is 0.5 degree elevation, and we have this number characteristic of the network. So we have 3 radar, m equals square root of 3, 30 degree separation, etc. With this parameter for this C-band radar, we would get an average beam size over this network of 4 radar and 2 network cells of 1,600 meters, and the minimum beam size on average 550 meters. So then, okay, let's suppose that we want to cover the same region with X-band radars, which have 1/3 the maximum range of the C-band radar. Let's say 50 kilometer maximum range compared to 150 kilometers. To do that, of course, we need a larger number of radars. So in this case, we will need 16 radars instead of 4 radars to cover the same region. And this will make up 80 network cells as opposed to 2 big network cells. So then we do the same calculation for this X-band radar. And so it will be here. Okay, so this is the C-band radar. This will be the X-band radar maximum beam. Beam width at the maximum range is depicted here. And with this parameter, we get an average beam size of 500 meters and the average minimum beam height of 60 meters. The minimum beam height is the height of the lower boundary of the beam. So it's this. Okay. So the beam height also is a nonlinear function of range. This is an approximate equation, but actually you could see this picture goes increasingly higher nonlinearly. So it is whenever it is very important to have observation near very close to the surface, like for example for tornado detection, then it becomes very important, and it may be preferable to have a network of smaller radar that allows, as we have seen in the example before, a very low altitude sampling of the atmosphere compared to one or few larger, longer range radar that will not provide such coverage in the atmospheric layer. So the other point, until now it was only geometric consideration. The other very important point, as I said, is sensitivity. So once again, we've been seeing this radar equation many times during the week. So one more time, this is the radar equation with all the elements in linear units, and this is the radar equation with the C, all those constant summarizing the radar constant in logarithmic unit. And you remember the radar equation of this lambda square. So there is a dependency of the received power on the wavelength, and it is quadratic on the wavelength. So it is very important. For example, if we consider the ratio going from X band to C band or from C band to S band is about a factor of 2. So when we go from X to C, it's actually 1.7, almost 2. Which means that when take square, there is a factor of 4 in the received power, which means that X band radar will have about 60 dB better sensitivity compared to C band radar, leaving unchanged all the other parameters. In the same happens when you go from S to C. That is, C band will have about 60 dB better sensitivity with respect to S band. And this equation allows to actually consider this network effect and take into consideration how this sensitivity spreads over the network. So, but in addition to this, of course, we have to consider this because if you are comparing, like in the example before, 2 C-band radar to 16 X-band radar, in addition to this, we will have to consider the gain in sensitivity due to the different frequency. So this is a comparison for the sensitivity, assuming the same radar constant in this case, so not considering the lambda change in sensitivity. And this is for the 4 C-band radar, which lead to an average mean sensitivity of 0 dBc on average over this region of the network cells. While with the 16 X-band radar, we will have an average of minus 10 dBc over the same region. Of course, if we consider the frequency difference, this means that we can actually further reduce the power of the X-band radar to achieve the same reflectivity of the C-band or even better. There is a factor of 10 here. So, for example, even the same radar constant, we have a factor of 3 for X-band. Then we can further reduce the power by a factor of 10 and still have a similar sensitivity. So then one may ask, so what is preferable? You know, one C-band with a very high TX power or X-band with cheaper and with low TX power? Of course, I don't have an answer here. It depends. Depends, of course, on the other cost, mainly the installation cost. For example, in urban areas, the cost of land and infrastructure in general is very high. So we've been seeing, we will see tomorrow also in Mumbai. I mean, that would be another nice example of for radars. If you give me the coordinates, we can update the presentation. And it is also convenient to have a cheap radar with a relatively cheap radar compared to long-range radars. Then in complex orography, this is even further enhanced because due to visibility limitation, it may often be not worth to invest in very expensive long-range radar, which will have sectors blocked. So it may be more convenient to have shorter range radars in that case. But although, of course, the answer must be searched, of course, case by case, it is useful to have some objective and characterization of the network overall characteristics to have some number to compare and help in the decision. Of course, one more, this is about trivial, of course, but the redundancy. Because if you have a single long-range radar covering a network set, you can imagine, a coverage of an urban environment like Mumbai. If you have a single radar here compared to 3 radar, of course, if one radar goes down, in one case you have nothing, in the other case you still have coverage of your target area by the other two radars. This is of course trivial, but of very high relevance for operational applications. Okay, now I switch a bit, from this geometric and sensitivity consideration and talk about type of networks. And actually divide the type of networks into two general categories that we call data pool and data push. In general, most national networks are what we call data push, which means that there are radar systems composing the network that have not any relation between each others, except that they actually operate the same or similar scan strategy and send data that are later acquired and aggregated. So each radar operates independently in a finite set of parameters. This is an opportunistic network in the sense that there is no feedback from one radar, other radars, or to the operation of the network in general. On the other hand, we have data pool networks that means that all radar collective operational strategy, and in which observations collected by one radar can contribute and feedback to the operation of the other radars and to the network as a whole. These include the adaptive scanning strategy, so which means that the scan strategy of the radar is not fixed, but it is adapted depending on the weather, for example, or on user needs. For example, if there is a storm in one direction, one radar can tell another radar to change from volume scan to sector scan to get more frequent observation in a specific sector. And I will have an example of CASA radar after that. And this is a very a general diagram with a very broad definition, trying to describe different radar networks in terms of radar density, going from sparse to very tight, and adaptivity, adaptive scanning characteristics, going from data push, which is no adaptivity, to data pool, which is highly adaptive. So in this kind of diagram, we see that national radar networks are in the lower left in general, while we have examples of especially emerging expanded radar networks going in the right and upper right, which means composing very tight networks. Of course, a tight network of X-band radar can still be in the data push mode, can be operated like traditional big networks, or can be adaptive, like in the Castan example. And then, of course, the research radar that very wide area that can be operated in very different ways. So here we have put the Nextra a bit higher in the diagram with respect to the Opera. For example, Opera is the European radar network, because most European countries operate the radar network with extremely fixed scan strategy. Scan never changes; it's the same all over the year, dependent on the type of weather. While Nextra is a bit more adaptive, in the sense that this is a coverage of the radar network. You know this. They have some degree of adaptability, which is not automatic. This is there are operators that, depending on the weather, decide which radar scan to use for every single radar. So they have a number of scan strategy, VCG, they call it. So, for example, you have a clear air mode when there is no precipitation. They operate high elevation every 10 minutes, very slow to get, for example, Doppler from clear air. And when there is precipitation, they have typically 15 elevation every 6 or 7 minutes. So this is a sort of adaptability, even if it's not automatic, but it's a level above, having the same scan strategy all the time. Then we have another example. This is a Japan network. On the left, in Japan, they have the National Japan Meteorological Agency manages a network of 20 C-band radar here. But besides this, they also have a very dense network, especially in urban regions, of 38 X-band radar, which is managed by the Ministry of Land and Infrastructure, Transport and Tourism, mainly for flood control and disaster prevention. And you can see that the density of the network is not uniform, but it's mainly concentrated in highly populated regions. Another example, in South Korea, we have 3 X-band radar here. And interesting, they operate this radar with a very frequent refresh period. They do only 3 elevation scans, but every 1 minute they have a full refresh. And this is, of course, for one flash flood prevention and precipitation forecast at very small temporal scales. Oh, then we have Italy. We have this network in Italy. Originally, the network was only C-band radars. We have a total of 25, 7 radars. And more recently, 2 fixed X-band radar have been installed here in Milano. And there are other several transportable radar that are deployed mainly at airport locations. So it is actually, slowly evolving towards a kind of hybrid network with the integration of both C-band and X-band radars. So this is the example I was anticipating before for CASA. IP1 in Oklahoma shows very well the concept of adaptive scanning. You can see all these sectors actually identify how each radar was scanning for every frame in this loop. You can see that depending on the weather being detected, the radars are commanded to operate different scans. See very well, in addition to sector scan, volume scan, they were also doing RHI scan through the core of the storms. So this, of course, this adaptive scanning strategies allows to increase dramatically the frequency of the observation. Because if you have a storm that is not very close to the radar, you can observe it within a very limited angle, maybe 30 degrees, compared to having to sweep the whole 36 degrees is a huge save of time. And you can actually repeat this scanning very frequently. Of course, when the radar gets close to the radar, you need to make a full scan, but other radars in the network that will be farther will do only sectors. And this will allow to have a network update the order of 1 minute. After the first CASA deployment in Oklahoma, there was following in Texas, this case with more 8 radars in an urban environment. So the rationale was measuring precipitation closer to the radar, closer to the ground in a highly populated region, urban area. And in this case, you can also see the next coverage here, of the higher resolution of observation and redundancy provided by a network of many small short-range radars. Then this is another. Yeah, sure.
So in this network, very good success. Mainly because in this Dallas network, we had very excellent success seamlessly integrating rainfall from national radar and local radar, mainly because it's all flatland. The melting layer is very high, the physics helps us, and the topography also helps us.
Yes. On the other hand, in this other project, This is in San Francisco on the California West Coast. Things are more complicated than in Oklahoma because we have orography, we have sea, and we have visibility issues. So this program is AQPI, it's the Advanced Quantitative Precipitation Information, and which aims to provide weather radar data precipitation estimation and short-term forecasting on the coastal bay, of course, to prevent to predict and prevent inundation from extreme storm, especially the atmospheric rivers related storm, which are huge amount of humid air coming as rivers in the atmosphere and bringing a lot of precipitation, mainly due to the interaction of this humid flow with the mountains in the just over the coast. So, in addition to the current coverage is provided by 3 X-band radar, the national network, NEXRAD. You can see in white, there are 2 NEXRAD here that are located at very low altitude, mainly at sea level. But as you can see, these are behind these mountains, and the visibility over the coastal region is very limited. There is another NEXRAD radar here. It's located at about 1 kilometer altitude, so it has good visibility, very few blockages, but due to this height, of course, also the observations are very high above the surface in the coastal region. So by introducing new X-band radar, the aim is to be able to provide better coverage of the lower 1 kilometer atmospheric layer. And in the future, there will be also an additional 4 fifth X-band radar, and also 1 C-band radar with a longer range with this network.
Sir, I have one question.
Yes.
Anyway, it is audible to all of you. So I just want to know that the similar situation we have over our region, it's a coastal region of Bombay and the Mahabaleshwar. Similar thing. So in this region, I'm seeing you're covering with the X-band radar for the orographic region. Why not the C-band radar? It would cover more of the sea surface region along with the inland region more, because at least at the top of the mountain, you are giving X-band radar for the city because the tall towers are there, it will be having some effect. But for when you put it at the top of the mountain, why you're not putting C-band radar network that will have not so much blockage at the top of the mountain, also it will cover a large part of the sea surface.
Okay, so my answer would be that yes, there will be 1 C-band radar here, but we don't put on top of the mountains because we want to sample the very low level. For example, we already have an extra here at 1 kilometer. There's a good visibility, but it doesn't see what happens below. We have example or processes like I've shown before of warm rain processes going on in the very few hundred meters close to the ground, and putting radars on top of the mountains will not have to detect these issues. And also there is probably also an economic factor because X-band radar are cheaper. You can actually you can deploy in regions even if the visibility is not very good. I will show you that some sectors are blocked for some of this radar. You see this radar here. The sector to the east is almost completely blocked. But since it's a relatively cheap radar, you can. You don't need to have the perfect site. You can deploy, and then if the visibility is not good, you will deploy another one which will cover another sector. While for longer range radar like C-band and S-band, you want to have a site with very good visibility because otherwise it does not justify to such a huge investment to have only one sector available. And actually, I think I have a few slides, some slides where you can see this. This is actually a visibility analysis from all the radars. So if you consider the NEXRAD, the colors actually indicate the height of the lowest available measurements completely free of orographic blockage. So of course, depending on the mountain, if I have the mountain, I have to increase the elevation. And then you see all this variability, which is related to the mountain ranges. So from TBBX, for example, you see that over the San Francisco Bay Area, we have observations around 4 kilometers above the sea level, which is very high. From the other radar, KDAX, a bit better, but still 3-4 kilometers, depending on the location. And from KMAX, which is the radar at 1 kilometer altitude, we have less blockage. You can see that there is no blockage here. The increase in altitude is simply due to the elevation. But of course, since the radar is at 1 kilometer above sea level, the observation, of course, are quite high. So this is the network visibility over this our APPI region, only from Nextral, which means taking the best at every point from all the Nextral, we get this picture. And you see that over most of the domain, we don't have visibility below 1.5 kilometers. While with this new additional X-band radars here, we are able to get information, even if not over all the domain, but on the much lower altitude. So this is the next step. This is when we add the X-band radar. So we go with this, which is our aim is mainly this region, San Francisco. So we see
This also you are getting like this also you are getting like 800 meters.
Yes. This is we actually get even less than 400 meters in some.
Yeah. Close to the radar, right? Yeah, little bit like 800 meters. Okay, so because we have the similar kind of the things like one S-band radar is there, it is covering entirely. Then C-band radar is there, and then we have 4 X-band radar. So the merging of that data looks easy, but just good, but like technical difficulty we are facing, first of all, the beam width is totally different because our is a very small radar, like it's 2.61 degree beam width, and C-band is like 1 degree beam width. So after certain distance, it will look different thing. That is one. And now you have given one example of Korea. They are doing very fast scanning within 1 minute, but our traditional things are taking like 6 minutes. So can you suggest something so that we can do all those things? Because in Mumbai also, I think Professor Chandra has given exactly the similar kind of the plot. We are even with our X-band also with so many clusters, we are getting like 1.1200 to 1600 meters. Yeah.
Yes.
So how to deal with all those situations? Because this curve looks very much similar what we have.
Yeah, we are dealing exactly with the same type of challenges in this project. And I think that first, the idea we do not pretend to have all the radars synchronized. And actually, but this starts from the same fact that the next radars are not synchronized among each other. Every radar they don't start like we do, for example, in Italy at 00, 05, 10, 15. All the scans are synchronized. Next is not like that because every radar is managed independently. They can operate different scans, different duration. So they're not. So there is a problem of time synchronization, even considering the next alone. Then the X-band radar operate more frequently, about 2-3 minutes in this program. So I think the different refresh frequency is not a problem. We are dealing with it by synchronizing the observation from every sweep of every radar to the same reference time and then integrate it. Of course, when we have real updated observation, we have updated observation, but at some time, the observation from radars that operate at longer repetition time, of course, will will be repeated and not back. But I have maybe an animation that shows that.
So we have to take like the similar time frame, same time frame you are suggesting.
Yes, what we do actually, we say that minute we want the merged product at minute 0, 2, 4, 6 every 2 minutes, and every at the reference time we had vect all the most recent observation from all the radars to that reference time.
You are doing that. You are doing that mosaicing at like what, all elevation.
The lowest elevation, so
Well, now we are focusing on QPE products, so we are doing a QPE product, not like CAPIs or other products.
okay.
So of course we rely mainly on the lowest elevation.
Okay, because if higher elevation, then it will be another more complex another. And how you deal with this sampling thing, because like X-band radar may be like in 50 meters or maybe less than that also. But C-band radar is typically like 250 meter or 500 meters. So you, how do you do that kind of down sampling? And
Now actually we have set the composite product resolution, which is 250 meters, and we get all the information from the radar to that resolution.
so basically you are feeding the C-band resolution with your X-band resolution. Is it like that?
I see.
C-band resolution is like 250 meter resolution.
Uh-huh.
So your X-band is also 250.
No, 250 is
Not correct, because this resolution is mainly changing. So there is a resolution of sampling data and then a resolution of observations. You can't mix up two things. You just take sampling.
Yeah, so that was my next question was like angular sampling and other thing like you have to put during. So that you also synchronize, like we should have like,
No, we don't.
like we
That can be
like
adjusted. It's 250. You just take a front and we work with the hydrologist. They're happy with the 250 meters. So then we go to 250 meters and then later we change to 100 meters. In Oklahoma, not Oklahoma, Dallas, Fort Worth. We did 100 meters. Okay, it's like basic, these are things that you need to fix. But you just choose something and fix and work. That's all. Right?
Something average almost 50 meter and that is 250 meter. So you take the 250 meter thing for that 50 meter.
Yeah, but that's the details of the sausage making process. There are so many ways. You just pick one and see what works. But what is important is not constantly handling and let's say, I'm going to put data. First of all, polar is an unnatural way of sampling that came from radar. So you just put it on an XY. In fact, some of the data plots there. You put a lot of the plots at the lat long grid. So you just have to make a sampling grid and then build data there. You have to build an underlying framework, common framework. So 250 meter, it's like just based on beam width, and that's like all old way of thinking. You just have to pick something. No matter what you pick, closer to the radar, it will be oversampling. Beyond the radar, it will be undersampling.
Yes, this is a general problem. Even if you have only an extra radar, close to the 5 kilometers from the next one, you have like 80 meters in azimuth and elevation. But when you go 1 kilometer, you have 1.5 kilometers. So the resolution changes anyway, not only because it's a hybrid network. So it's the same.
Yeah, so
Yes.
this kind of the things is doable because these are all mathematically you can do.
Mm.
Physics point of the unit has so many challenges. So, okay, thank you.
In the composite visibility here, so you composited the max reflectivity or reflectivity at the lowest?
No, this is just a visibility composite.
No, in the mosaic product.
The mosaic, we do both a maximum reflectivity and a QPE, I mean, for a rainfall estimation. In the rainfall estimation, of course, we give large weight to the lower level observations.
And then the rain estimation is from the max reflectivity.
No, from the lowest level.
Lowest. So you will have 3 different products: lowest level mosaic, then composite reflective mosaic, and the rain rate mosaic.
Yes, basically. Yes. So this is the statistics in terms of visibility from Nexar only, and to to the hybrid network, including the 5X band radar and the future C-band radar. So you can see how much we decreased the portion of the distribution of observation above 2 kilometers and improved the lower level sampling. Yes.
Right? Now this answers Kaustav Chakravarti's question. Like you basically asked, you put a big C-band radar on the top of the hill, blockage, all the problems are over. That's pretty much like Rajshekhar come and say, I have a big C-band radar that covers all the region. I don't even need the Mumbai X-band radar network. Right? So C-band covers all over Mumbai, right? Why do we need this? So many of our people will ask the question, you don't need this. So this figure shows why. Because without those X-band network, we cannot make low-level measurements. Right? Yeah, QPE is the problem, but QPE is the billion-dollar problem that drives the economy. Because monsoon, rainfall, water, it's a big problem that pays the bills. Severe storms. So in terms of the difference, that's what worked. Our focus was on severe storms. City, whereas here its focus is on water. That's why the name of our project is AQPI, Advanced Quantitative Precipitation Information.
Well, one more thing that in this case, I mean, we have to deal with the problem that during the rain season, which is basically from November until now, the freezing level can be quite low. So the metal layer is often below 1.5 kilometers. So without this new observation, we are often with an extra radar within or above the metal layer, which is a very huge problem for rainfall estimation.
You should be very lucky you don't have that problem.
You don't have this problem, but I'm learning that you also have a variation in below the metal layer, which is significant. So it can also be
useful to consider. This figure is self-explanatory, but it's like positive is left-hand side skewed, right-hand side skewed, and you
left-hand side skewed diagram, right-hand side skewed diagram. You join it, you get a perfect Gaussian, and then height will be like less than 1 kilometer. So that's the idea of doing this X-band radar.
Yeah. So okay, this is an example of local installation. This is one of the radar. So from this radar, as I said, they didn't have the perfect installation site. So you may have to deal with the blockages. In this case, there are blockages from trees, and so this is the worst case. This is one of the radar. This is the radar that has more blockage. And you can see this sector has many problems. So actually, what we will probably end up will be just cut completely this sector, and this will be covered by the C-band radar. It's currently covered by Nexar, and it will be covered by the C-band radar that we installed. It's just to say that, I mean, it's this type of installation, you will never have a perfect site. So unless you invest a lot of money, then you build a big tower to install a cheap radar, which probably makes no sense. But you just deal with it by installing another small range radar nearby. So then coming to some applications, network. When you have a network, you have the real-time possibility to compare observations from different instruments. So especially if you have a good overlapping region, like in this case, then you have a lot of co-located information that you can use to check the intercalibration of the radars. This is an example of network calibration in Argentina during the Chile campaign, where they had 3 radars. You have 3 C-band radar, and they were also using measurement from the satellite from GPM. So they established intercomparison procedure that is summarized by this pyramid. This figure, you have the three C-band radar on the ground, you have the satellite. So they actually compare on a Cartesian basis, in this case, the reflectivities between pairs of radars. These numbers is the bias between this radar and this radar. And you have the bias between this radar and this, and this, and between each of these radar with the satellite. Then there is, you can say that along each phase of this pyramid, if you turn around, the bias should be zero because you come back to the origin. And then there is a procedure to optimize this and to evaluate accurately the relative biases. We do something similar in Italy. We do it at the polar geometry directly, while the previous example was after regrading on the Cartesian and comparing observation, let's say the Cartesian grid points. We actually extract all from two radars. We calculate the intersections between the two sweeps. So actually the intersection between two cones is a line like this. And then we compare observations along these points. In this plot is summarize all the intersections. The grade of the gray shading depicts the altitude difference between the two radars because we don't want to consider only the things perfectly matched. We have some tolerance on the altitude and on the relative distance. So we get all those gray shading, which denotes the intersections between different elevation pairs. This figure we consider 0.7 degree for radar A, and we see all the intersection with different elevation from radar B. Of course, when radar B is higher elevation, you can see it becomes almost circle. Because radar A is low elevation, radar B is higher elevation, so the intersection will be almost a circle above this radar. So with this, we have a huge amount of collocated information that we can plot in this way. We do this every day to calculate the daily intercalibration. So we check this. This is the intercept, in this case 0.8 dB. So we can check whether one radar deviates from the other. And in a network, this is very useful to detect possible problems on any of the radar. And this is the density of the observation in space. With all this information, of course, we can apply different thresholds. We can apply a threshold based on the reflectivity near the radar to exclude from the comparison to measure where we think that one radar may be affected by random attenuation. So in this case, we removed the observation where we removed observation where it was raining on the radar B, in this case where it was raining on radar A. Of course, the intercept changes a bit due to the random attenuation on each of the two radars. And then we can, of course, remove from both. This will decrease the amount of data. So actually, we started from the order of 100,000 data. And of course, imposing selection of the data will reduce the sample. In this case, we went to 14,000, removing all data where it was possible that it was raining on either of the two radar. But then, of course, we have in general a better estimate of the relative bias. And also we can apply a threshold on the ROG to ensure that we are looking at the precipitation from both radars. And this is actually the time series analysis of this intercalibration with our two radars from 2022 until now. And you see that there is some variability. But in the end, we had an average of about 0 dB with a standard deviation of 1 dB. So in the long term, it is a very useful monitoring tool to assess the good calibration of the network. We are doing this because we only have two radar. We are doing two radar, but in a larger network, you can do this between each pair of radar and then do a comprehensive analysis. This is another possible network application for a single polarization radar, because when you have points in the network that have been observed by different radars, then you can compare the reflectivities at a common point. The reflectivities in attenuate, if you use attenuating frequency like expand, the reflectivities observed will be typically different because each radar will observe this one from a different path, so the path explanation will be different. And then you can apply a technique, which is the same rain profiling technique that been applied using PDP as a constraint. Luca have shown some example yesterday, but instead of PDP, you can actually consider the delta ZH, so the difference in reflectivity at the common points. And then through a minimization of the specific attenuation through an iterative process, you can come up with actually the true reflectivity at the point by minimizing the difference between the different acceleration after correction. So this is a possible interesting application. Next, and I think that I'm coming to the last part, we have our own examples. In Italy, in addition to the C-band radar, we have mobile X-band radar that is being recently deployed quite close to one of the C-band radar. This is Torino, Italy, and this is the C-band radar on the hill, 700 meters above sea level, and this is 15 kilometers apart is X-band radar. So this is the X-band radar on the trailer. This is a C-band radar on the hill. This picture actually is a view from this radar towards the location of this radar with a thunderstorm in the middle. So this now is a very interesting test bed for us because you see this is the scan of the C-band radar. We have 11 elevation going from 0.5 to 28 degrees. And this is the center of Torino, castle. And we see that we have, even with a low elevation, we have the lower 500, 600 meter unsampled close to the ground. And then we have this X-band radar, which operates only 3 elevation. And unfortunately, we have some tree blockage, which prevents from using very low elevation at the moment, unless in very few sectors. But with all this, we can again do this intercalibration thing. We can look for all the collocated information from all the intersections. Here you see only a section, but if you go to 3 dimension, so every point here corresponds to one intersection from any pair of scans from the 2 radar. Then it is also due to the very close distance between the 2 radars, and the fact that operate at different frequency, so it opens a lot of possibility to compare observation and even optimize algorithms for attenuation correction and rainfall estimation. I'll show you an example. I have on the left, this is the 7-degree elevation from the X-band radar, and on the right, 2-degree elevation from the C-band radar. And here you see the points. These are all the collocated points from these 2 specific elevation suites. And this is a scattered plot of the common points, on the collocated points, before attenuation correction. Then if we do attenuation correction using a simple PDP, delta PDP approach, basically where alpha is 0.85, alpha is given by table for different frequencies, and then we correct based on the PDP. PDP, this is filtered PDP. This is from X band. This is from C band. You see much larger value from X band, which is due to the scaling with frequency. Normally at X band, we see a larger differential phase increase, which is due to the, of course, to the higher frequency and smaller wavelength. And so after, if we correct for this attenuation correction, we get we go from this to this. So you see that now after correction, the plot looks much more similar, and actually also a scatter plot is much better. We actually went from say 0.637 correlation and a bias of -4 dB to 0.91 correlation and bias of only 0.8 dB. So, and using this coefficients, this table reports the coefficient for attenuation correction at different wavelength and different temperature. And we actually ended up applying these coefficients, which are actually very close to the ones that are calculated from scattering simulation for C band, which is about 0.1, and X band, which is about 0.3445. So I think this was. I have one more. I forgot about this. Still have 5 minutes. Yes. Any question on this?
Hi. Can you go back to the Argentina case?
To the
Argentina,
Argentina, yes.
Can you talk more about how you did the comparison and what's this bias? Is it after some correction or what is this?
So, but yes, you can find all the, it's not mine, you can find all the details here. So, actually, they calculated the bias in the arrow indicate means RMA minus CHIVO, no? And this is APR minus CHIVO. You look at the bias.
I'm interested between the KUPR, between the GPM and the ground radar bias, comparison. So how did you compare it? Like, did you perform any attenuation correction?
It's a whole big paper on how to exactly GPM.
Ground radar.
There's a paper, there's like a lot of, not saying details. You have to do volume matching, then you have to do attenuation correction, and then after that you make a comparison. There's like whole process. So it's all described in the paper.
Okay.
It's, you know, yeah. It's swollen and so,
What is the lead time of your AQPX?
What is the
Lead time
lead time for what?
forecast?
For forecast. So, I think we are running now cast based on the darts at 1 hour. 1 hour lead time.
So lead time is of 1 hour.
Yes. Now cast. Yes.
Yeah.
Yes.
Whatever, that lead time, I'm talking about lead time. So lead time will be the 1 hour.
you're doing forecasting.
Yeah, yes, we are also doing forecast with rapid refresh with her, and but the nowcast, I mean, the extrapolation nowcast based on only radar data, we now with up to 1 hour.
Okay. And the similar question I had that at previous that comparison of the GPM radar with your radar for the measurement of the surface precipitation.
So is this the same?
Yeah.
This, well, I don't. The comparison for surface precipitation,
Yeah, from radar and the GPM-based radar and the ground radar.
In this case, they only compare reflectivity for the calibration of the network. So this was focused on ensuring proper calibration of the ground network, and the idea was to compare the ground radar between each other and each of them with the satellite, which is a common reference. And then they came up with this scheme that involves both the intercomparison, the ground radars and the satellite. But there is no precipitation estimation in this application.
Is there any scope to compare that your snow melting with this precipitation type?
Yeah.
Yeah.
India has some papers. Ask them to look for India and some.
He said look for Minda and Chandrasekhar paper. Yes, I am not. I cannot provide that answer.
That's it.
I know that.
Yeah, yeah.
So I have a question. Network calibration of the Italian two radars. The mean which you had stated was around 0.05 plus or minus 1.1.
Yes, I think it's by chance it was so good over this period.
So around it is around like, at any given time if we take a difference that will be around 2 dB each.
Well, you see that there are oscillations. It actually varies between about -2 and +2, generally, depending on the events. But a single day is probably not enough to get. This is more for a long time quality assessment.
So what I was trying to ask is 2 dB, if we are off over a period of time, that is not a big deal.
Well, 2 dB is not dramatic for for a single day because it can be due to many different reasons. You can have you are looking at the precipitation from a very different view angle. So there can be propagation, anomalous propagation. You may actually be thinking that you are comparing the collocated cell, but maybe one is higher because propagation changes. So that's why this is very useful, but on a statistical basis, you cannot rely this. Yesterday I observed -2 dB. I correct for today. No, it's for a longer period quality assessment. But if there are some big problem on the radar, you can actually see day by day. If you have a problem on a transmitter, you will see this going down, but maybe 5, 6 dB or some other problem, we are able to detect on a single radar based on this Sunday. We can go to the last part, which is actually a few slides about data deployment in complex terrain, bringing one example from our experience. For a project, we had to deploy our mobile expand that you have seen before on a valley, Italy. So we did some visibility analysis to decide where to deploy the radar. So actually, we start in this case with the catchment because we want to monitor this hydrological catchment depicted by the gray dots here. So we ask how can we estimate the visibility over the catchment and choose a site that is the best visibility over the catchment. So we did this visibility analysis, basically iterating over the whole domain and calculating the visibility over this catchment from different positions. So if we actually pose no limits, but just ask that we have some kind of visibility of the network, we actually get all those small dots. These are all points that have some kind of visibility over the catchment. So you see that there are points even far away, only considering, of course, given distance, I think a maximum 30 kilometers from the center of the the catchment. And there are points, of course, behind the mountains which have no visibility at all. But then, of course, we want to restrict, we pose a condition of having visibility of at least 400 meters on average over the catchment. And in this case, we have only few points, these bold circles here. And we try to see if some of these be a good installation site for the radar, but actually not. Either there was no road or no power supply. So we actually relaxed the request of 400 meters to. Okay, this was the visibility from. Okay, just to show an example from one of these points. With good visibility, you can see this is the visibility from the radar. Again, the color shows the height of the beam, which is completely the first, the lowest beam, completely free of mountain blockage. And you can see that we are mainly in the blue portion, which means below 400 meters over the catchment domain, but this was not feasible for the installation. So we relaxed it to 600 meters. So the request were visibility of at least 600 meters. Of course, the number of candidate sites increased, and we finally identified one of these sites actually on top of the catchment on the mountain, and looking down from this, we actually have still a good visibility over the catchment, and we ended up installing the radar there, and it's been there for summer with the campaign. This is a valley very close to the French border, so this is Italy. If we look back, we have France, and from this, of course, we had a specific scan, volume scan, and also RHI scan along the valley, which was, this is the main valley, and we were able to also use a negative elevation to scan deep into the valley. This kind of observations. So with that, is I guess yes, it was a part.
Any questions? Let's hand Dr. Nenzuki. We have a short tea break and gather back at 11:30.
Take a seat.
Welcome back after the short break. There's a small announcement to make. Please submit the TF form by today itself. Next we have a recitation section on data quality monitoring examples led by Roberto Kimoni.
You know, I said in the beginning that one of the most important reasons we do dual polarization radar is 3 reasons. You remember the 3 reasons? You don't remember? Data quality, and data quality. So Roberto Cremonini is his full-time job to make sure data quality. And then he's also going to talk about next, where is our forecast person? He's missing. From that end, he was always asking about forecast. So early morning, how all these things work into user products. Oh, last second is missing.
The same place.
Awesome. Is this outside? Okay.
Sorry.
So
You said the
So these are all very practical things. So you need to really be wait again because it's important for IMD this topic. You can message it. we will wait till the application people come back. Huh? No, I mean, he's calling. He's calling. Is he far away? He's already left. But he would have faced, but it's okay. Yeah, there was a podcast person there. See, anyway. So please start.
Okay,
So this is Roberto Cremini. Give him a
so first of all, it's an honor to be here, and I wish to thank the organizer for inviting us for this wonderful workshop. Secondly, I briefly wish to introduce myself and my organization. So I'm a weather forecaster, meteorologist, and me and Renzo are employed in the ARPA. In the next speech in the afternoon, I will spend more words about our agency. So we are a public agency, government agency, and we are in deal with the issue warning. We are responsible for local weather forecast, so we are operational. So we are moving. We heard a lot of words and about weather radar research. Now we are moving to the application, and we are moving into the operational worlds. All data that you have seen from the C-band radar in Piedmont, in Italy, comes from an operational weather radar. This means that this weather radar operates 24 hours by 24 hours each day, except for maintenance. So I report my email if you have some question. Data quality. Data quality is mandatory. So in the early age of weather radars, we look at picture. We consider the weather data radar as a nice picture, useful for weather forecast to locate thunderstorm, incoming rainfall, and so on. But then, starting from the 80s, we moved to QPE. That means quantitative precipitation estimation. I may talk about, I forgot one detail. I'm also a lecturer, I'm a professor at the University of Torino in meteorology. So I get used to make questions. Why we talk about QPE estimation and not QPM measurements? Some students can answer. Why estimation? Yes, because it's a remote sensing technique. So for this reason, we do not measure directly rainfall intensity or rainfall accumulation. This is a key point because at the end of the story, there will be a needed comparison with rain gauge. So data quality is relevant if we want to move from a nice picture to data, to estimation or measurements. Nevertheless, data quality is an abstract concept. So we have to think about data quality related to the application. Yeah. For example, if we are interested in ZDR columns, for example, we are typically looking aloft. So there is no ground clutter. So no ground clutter is expected at 5,000 meters above the ground. So the concept of data quality has to be seen in the sides of the application. Oh, requirements. There is a lot of literature, and you can find these numbers in the chapter 7 of the famous book. And so this is the requirements for measurements. So we expected that reflectivity is within 1 dBz, velocity 1 meter per second, spectral velocity 1 meter per second, z at 0.2 degrees, and 0.01 for Reuschel. So this is our requirements. So these are instrumental requirements to be sure that our measurements are good enough to expect good QPE. And I come back from a famous equation. So the problem is to be sure that all these quantities are good enough. We have to measure, we have to be certain, we have to be sure about this. Okay, so the radar constant. So we have to keep track about the value of radar constant during the time. And we saw some technique. And during this talk, we will review most of them. And yesterday we met this technique. Yeah, the calibration by sphere. What is the drawbacks of making this calibration? I don't go back. So yesterday, Renzo gave you whole details about this technique to get the radar constant. I want to give you other information. What's the drawback performing these kinds of calibration? So it seems perfect. It seems wonderful, but which is the drawback of this? Any idea? You have to switch off your operational scan. So you need the time. For example, this is a practical problem. You have to set up these experiments. So the second drawback, it's according to your radar site. If you think about a radar site that is located on the peak of the mountains, and you have to make a sphere calibration, you have to be far from the radar enough to avoid the TR limiter interference. So 4 or 5 kilometers. But then you are in the peak of the mountains. So it means that all the other locations are well below the radar site. And you need to get the lowest elevation of your antenna. So that's could be not so easy. And also there is another environmental phenomena that affect these kinds of measurements. Can you imagine what is? So we expect a clear day, a wonderful sunny day, but wind and turbulence, because in this case the target is not well located, is hard to locate in the space. Yeah, so this is a good, this is the most wonderful way to estimate radar constant, but has some drawbacks. There is another chance to make other way to calibrate the radar constant. At least we think about, we talk about relative calibration or partial calibration, because we can consider the sun. We know the exact position of the sun. We know the amount of radiation coming from the sun. So we can point our antenna into the sun, in the direction of the sun, and then we can measure power. And which part of the radar is missing in this story? Transmitter. Obviously, we cannot, but we cannot measure the transmitter power quite easily by electronics and making some measurements in the other side. But the advantage of this technique is that we can measure, we can calibrate or even insight about radar calibration for example, without changing our scan strategy. Because we are quite sure that during our ordinary scan, we will meet the sun. And if we collect data for several days, we get this plot. And this is our real data, actual data. So you see that, okay, sometimes, so there are some issue, there were some issue here, then radar calibration, and then maintenance, and then it went better. About sun calibration, I wish to cite, to refer to some unknown editors that in the 2011 make some assessment on the sun calibration technique. So this is one well-known technique that is fine because it can be performed without affecting the operational scan and can be done every day. Another relevant aspect of the sun is that you know the sun position, and then, as I told you, you get the sun power, and then you can estimate the antenna pointing accuracy. Even so, you can also get information about elevation and azimuth accuracy, or eventually errors, and then you can set up a maintenance. The solar flux numbers come from Canada, from Draw Observatory, and this flux, pay attention that these fluxes are for S-band. Then you have to convert it to C-band or X-band if you are considering different weather radar. There is another chance. Another chance is ground clutter. It's a signal coming back. It's something that we typically don't want. But if you get measurements every day, you can get a signal. You can consider the overall ground clutter over the radar domain, or you can spot some well-known target, tower, for example, buildings, something peaks. Again, you can, without modifying your operational scan, you can get data. Again, this technique is similar to what Renzi told about relative intercalibration, because again, you can get information. You see the spreads, and here there was stopping the radar, and then there was a maintenance for an antenna problem, and then it restarted. It's useful. This technique is useful to see large miscalibration. So problems that occurs in the radar due, for example, a loss of power in the peaks, or some waveguide losses that increase. We observed in the past, we had a trouble several years ago with minus 10 dBs in the weather radar due to a problem in the waveguide, and we were able to catch the problem there. And also, it's interesting because it works every day, especially even in clear days, sunny days. Because the problem with the weather radars is that you don't see rainfall signal until it rains. And then maybe you can discover that your radar is not working properly just when you need it. That's So about these topics, Renzo almost explained. I want to add only, yeah, this distance, those are our two radars, and this distance is 90 kilometers. And then here are the plots, but we discussed early. I don't want to spend more words about this. And there are other techniques from this, but for example, you can compare Cartesian reflectivity of logos being by two different radar. So in this way, as we heard before, there is the assessment about co-located point. When you make an intercomparison between two Cartesian map of two different weather radars, you are not sure about the altitude, and you are not sure about the exactly co-location of the points. So this means that you will expect, if you make the same plot, the same scatter plot for starting from Cartesian products like QPE or lowest reflectivity beam by two weather radars, you obtain a wider spreads in the regression. Accuracy. We touched yesterday this topic. We discussed about the number of pulses. This is as Chan says yesterday. When we got single polar weather radar, we don't care too much about the number of pulses, but the with polarimetry we require also a good number of pulses, integrated pulses, to get good quality data. So, except for this formula, I want to, if we focus here, this is the number of samples, this is the dB uncertainty, and this is the spectral width. And here you see how the uncertainty, how the accuracy improves as you increase the number of pulses. Which is the
So this is a very interesting plot. This is from the simulations of.
Yeah, well, this is from theoretical. Yeah, this is from these formulas. Yeah.
And this is for as well.
Yeah, but it doesn't change. Yeah, it doesn't change.
So what I can understand, like 80 samples if you have, so then it is a good number that, because after that it becomes almost steady.
Okay. As we can see here, so there are two things to highlight in this plot, but yeah, I would prefer to here is bigger the picture. Okay. Here you see that there is a steady decrease as in the initial parts of the curve, and so it means that when you go further, your improvements is not so much.
Yeah.
Which is the payback for the pay? Sorry, not payback. Well, what you spend if you wish to integrate a huge number of passes? What do you have to pay? Money? Time. Yes. So to get a larger number of passes, you have to spend time. But if you are in convective, which is the expected repetition time for tracking a thunderstorm? What do you expect? 1 hour? Half an hour? 15 minutes? 5 minutes? 5 minutes or less. So our time is limited to this. So And how to save time? Move faster. So to turn the antenna faster, we will see later the expected number of mass. There is, but there is a good news. Look at this curve. There is the expected uncertainty is dependence on spectral width. So what does it mean? Because when we got by weather radar a good measurement, we expected, which is the condition on the sample. They are independent. So we expect the independence between sample by sample. What can assure us the independence or improve the independence by sample by sample turbulence? And so if there is a lot of turbulence, if the turbulence is increasing, then the number of samples expected for given the same accuracy can reduce. Did I answer?
Yeah, so what you are saying is absolutely true, but we are just wondering, like after 80 samples, so suppose if we put like 100 samples, and after that, that doesn't make any change because it's like a steady line.
Yeah.
So
Yeah, we don't. Yeah. How many samples from brick 66 or?
Convective environment, since there are the spectral width is more, we will get good independent observation. So we can have lesser number of samples and move the antenna fast.
But there is another advantage, not only in convective. The turbulence is increasing, the spectral width is increasing, coming along. So it means that your antenna can turn slower at the lowest elevation and faster at the highest elevation due to this fact.
Yeah.
And this is a technique to save time. Can you hear me?
yeah,
Sorry, I don't know what's that. Does it work?
So the number of samples remains same for different measurements, Z versus ZDR versus HG, or can we also change that?
No, the number of sample is okay. So indeed, it depends on your hardware. So if you use power switch or a simultaneous, so for variable for parameter variable, they change. But if you use simultaneous transmission and series, it's the same. And but there are additive troubles when you go to very low number of pulses integrated. So you have an additive bias, and here you see how the additive bias change given the signal to noise ratio, and this is calculated for PLF of 1000 for S-band. Again, the turbulence is playing with us because it makes sample more independent and then improves the data quality. SQI is the typical filtering for bad or good quality data. Yeah, you see, SCP is the same as SQI. I know the guys, and then I'm calling it SQI. This constant is almost 1, and the thresholds of SQI is running as 1 as the square of n, where n is the number of pulses. If you try to make a simple calculation, typical n could be 50 or 60, then you can get the threshold, the expected thresholds. So SQI is the typical thresholds below that your system provide no data because the data quality at radar system is too low. How much pulses we are able to integrate? Oh, this is the simple formula. If we consider the antenna beam width, the PRF, and the antenna rotation speed, root per minutes, and this 6 comes from this root per minute. Oh, we can calculate. Which is the bandwidth of your weather radar? C-band 1. So this is good enough. If we consider 1 degree beam width and a PRF of 1,200 with 3, that means 18 degrees per second. How many samples? Somebody is able to make calculation? I cannot hear. I cannot hear the number. How much is? See. Yes. Do we need artificial intelligence for this? Yeah, the guys there. How much is 66?
Yes, just use your cell phone.
67, 66. Yeah, because the 66 not. Yeah. Okay, how can so? Oh, this is in a scanning mode that is called the angle slinger. So this means that the weather radar is integrating only pulses within the bandwidth. Otherwise, yeah, you get strange. Also, with polarimetry, you get a really strange data. Yeah. So how can we improve? So the number of pulses. Given that formula, how can we improve? Scanning is slower, but the drawback is that it takes more time. Or yeah, but the drawback is the velocity is good. It's not a drawback. If we can an ambiguous range, yeah, that's the problem. So the problem is the drawback. Yes, and also you get a limit because when it's depending of your transmitter average power emitter. So this number cannot rise to the infinite. Yeah. So yeah, we can increase PRF. We can increase the antenna speed. So I want to explain. We can save time increasing the antenna speed as the elevation increases. Plain gain to the fact that turbulence makes a sample more independent. So we can define a scan strategy where the lowest elevation scan slower. Meanwhile, as the antenna rises, then you get, and you can save time. Yeah. Oh, with polarimetry and with the proper number of passes, rho HV, we talk about SQI. SQI was the quality thresholds related to single polarimetry polarization weather layers. But with the dual polar weather layer, we have also rho HV that is a good indicator, given the signal to noise ratio, is a good indicator of data quality. So it can be used. We know that in the rainfall, it gets very, very high values, 0.99, 98. And then we have, but we have also some drops. Yeah, I want to show you. This is an X-band RHI made in a thunderstorm. And you see the thunderstorm was moving toward to the radar. And here you see a drop, but it's 0.95, 0.93. Why? There is a drop on the back. Have you an idea why there is a drop in rho HV thunderstorm? Do you remember the air contamination? Yeah. So, but nevertheless, you see that so the relative value. So the value of rho HV is very high. Then it can be also used to be sure that your data comes from hydrometers and have a good quality. This is the same that Rainfall made in the intercomparison between the two weather radars. He selected cases with rho HV greater than 0.94. That's signature. So we discussed about also the wideband and rho HV and so on. Well, I wish to ask you something about what is this? Is it a thunderstorm? Who believes that this is a thunderstorm? Raise the hand. It's a cluster. Yeah. How can we identify cluster? Oh, from a general point of view, in this picture, we see ZDR on the left, and we see a rising value with this circular form. So this means that which kind of precipitation is this? Stratiform. And this is the bright band. So we do not, first of all, we do not expect a thunderstorm. But there could be some convection event. But if we look at rho HV, we see what's happening. Yeah, it drops. It drops below the, yes, this number is 0.7. So if we go with rho HV below 0.9, 0.90, then we can issue about, what's flowing. And then, what is this? Ring blockage. So this is an X-band from Lombardia. So this is in the Po Valley. Sorry? Yeah, this. Yeah. Can you imagine? It's a Doppler filter. That is not good for. So what's going on? So you can remove in the single polar weather radars. We used to remove ground clutter given the velocity. So at the level of signal processor, if you have a velocity close to 0, then the signal is removed because it's thinking that is cluttered. Okay, so this is called the Doppler snake. Snake, yes, because this line, and I like the line. Now you can see clearly. Thank you for your question. This is Interesting. So it's the zero Doppler. Yes. So with zero Doppler, the signal processor believe that it's clutter, and then it removes reflectivity, horizontal, vertical. But this is not. So another measure, another message for operational weather radar in polarimetry: get all the variables. So corrected and uncorrected. So uncorrected means that if you apply a clutter filter, polarimetry, and all variable are, you get also the original values of this variable, because otherwise you lost something. Because clearly this is the clutter filter remove some weather signal. Yeah. Okay, we talk about the instruments, but if you want to move to QPE, we have to also consider the environment and what we are measuring in the environment and which type of phenomena or situation or occurs that affect our estimation. And we must be conscious about this. Well, this picture comes from the Deutsche Wetterliste, so the National Weather Service from Germany. And then you see, if we move from the radar, things that can affect our measurements is rainfall over the radar. We saw some cases about calibration, especially during the sphere calibration. We make the experiment wet in the radome, and we saw that these water films can attenuate at the C band, especially at the X band, can easily attenuate the signal. But there is also, okay, deadline, I don't know, in India, the 5 gigahertz at C band is very dramatic in Italy. We have also birds, insect, windmill. Do you have a windmill? Yeah, also windmill is because the traditional clutter filter cannot remove because it's not seen as zero velocity, and then you get this signal in your weather radar. Then happens other large drop, the difference of hydrometer. We discussed a lot about DSD, large drop, small drops, but also snow is another problem obviously in the mountain region. And we will discuss about it. And sometimes you overshot. So you take measurements, and the rains and the relevant phenomena occurs below. That's the reason why cars are developed. So when we talk about QPE, so which is the definition of rainfall? We could discuss about rainfall accumulation or rainfall intensity. Which is the definition? Who is better? So it's the amount of water per unit of area reaching the ground. But if we measure here, between these measurements and the ground, there is space. There is a distance. So something can happen. So this is justify why we have some uncertainty, and we talk about QPE also. This is our weather radar. This is a relatively old picture. Yeah. And you see all, if you look at only reflectivity, it's making it quite hard to recognize weather and clutter and so on. Here it's quite clear. Really, really strong vehicles are ground clutter. Here there is precipitation. But sometimes you have also some ground clutter contamination. Then towards the Alps, you have a beam blockage. And why you see this? Yeah. this feature. How to call you this feature? Why the reflectivity is so low here, and there is this sharp increase moving towards this one? Is it natural? Is it? Yeah, this is partial beam blocking. So you have still you have some signal, but yeah, you get the less signal due to the mountains, and this is a topic of that we will deal. And okay, this is a PPI at 1.2 degrees, and yeah, the number of samples here was 40. And then why there is no signal here? So it means that here this is Milan, and this is Pavia. So this is Milan. It means that it's not raining in Milano. Yeah, our beam is too high, and so this detection has a seasonal behavior, because when you have a cold weather, and I'm thinking to northern part of India, obviously, not the southern part, but when is the cold season, so the thickness of precipitating clouds is thin, and so you lose the chance of observing something. We talk about unambiguous range and the radar Doppler dilemma. So you cannot get at the same time good wind measurements and far to the range. But you can identify. So this comes from Hong Kong Observatory. This is a sea clutter. What is this? Again, a signal that has a radial feature is not natural. It comes from something else. They are also called artefact in the weather radar. So because you see something that does never exist. What's it? So this such shallow echoes, weak echoes, and radials are the common feature for second trip echoes. So it means that there is a thunderstorm, a heavy thunderstorm far from the radar, beyond the maximum range, this one. And then what's happened? When the second pulse started, the first pulse hit the target and come back. And when it come back, it's confused with the second one. So in the traditional weather radars, now there are some technique to remove at the level of signal processor, like signature in the pulses. But the easiest way is the radial form is shallow, because yeah, only lowest elevation can get, because as far away, our beam is very tall respect to the clouds, and only the lowest elevation are able to catch this severe thunderstorm so far away. Far away, I mean 300 kilometers and so on, 500 kilometers. Depends on your scan strategy. Well, this was a cipher. Yeah. Yeah. Oh, this is a problem of C-band. Again, another picture, 2008, September. You see our weather radar is here, and then the beam propagates in this direction. Here, what's happening? You see, our C-band have to pass across two thunderstorms. So the attenuation became so big that we get the signal extinction. As I told yesterday, suppose, or even Monday, when there is extinction, there is no, no other chances. There is no signal processing that can improve your missing data. And so this is not, so this could happen at C-band, even at our lecture. What is the joke about this? So it's a joke about geometry. So the unlucky chance that the beam had to cross 1, 2, 3 several storms at the same along the path. So how can you avoid this missing data? One chance is increasing power. So this is also called the, I would call it the Russian solution, because they had the transmitter of incredible power in the past. Yeah, this is one chance, but another chance is add radars. Have a network. Yes, that's the only solution. Because if you have a network, so to have a missing signal in one place, it means that you are so unlucky that all the tensor systems are located in the exact place to blank to blind all the weather radar at the same time. There is no chance for this. No. Oh, we already talk about weather radars in the models. Again, I refer into the complex orography that is also here the case. So this comes from our neighbor, Swiss weather service, Giuliacci, then Boscacci, sorry, German Boscacci and others. And I took this picture from this paper because it's cool, because so Swiss is a mountain, is almost 100% mountain region. And then the weather radars like ours also are in the over the peak of mountains, some of them very tall. And then you see how the scans, the scan behavior for different weather, they have 1, 2, 3, 4, 5 C-band radar operational, and this is the parts, those constitute the Swiss weather radar network. And here, according to their scan strategy, you see the observation related to the ground. I'm introducing this topic because you see that in some cases, so the scale is 8 kilometers. So some cases you have an observation at 3, 4, 5, 6 kilometers, but you want the QPE at the ground. So everything happens in the middle. Again, as demonstrated by previous talk, the chances to add weather radars, obviously in the Alps is not so straightforward because it's very hard, complex orography. But in other places like Mumbai, you have this chance. But so we are lost, and we want to see other. Oh, this is another case. This plot comes from the open source WRAD by Python. Yeah. So this is as mentioned by China. This is a C-band radar installed at 3 kilometer altitude over the Alps, and this is the Olympic game place for Dunning. So in a collaboration with Lombardia, with another government agency, we support them. And then this is the expected beam blockage fraction for the first elevation. And here you see, so the Dunning starts from here and goes here. But what is interesting is to see that the distance from the measurements at the ground can vary a lot. And so this means that in principle, it's hardest to measure to have a good QPE in the complex orographic complex. But we, from this such theoretical calculus, obviously when we have beam blockage, full beam blockage, there is no chance. But if we have partial beam blockage, from theoretical calculation, from this kind of map, we can correct data from this beam, partial beam blockage. So if we are in stratiform precipitation, then we have bright bands, then we measure. Then in sometimes we measure with the right QPE from an observation that is above the bright band. So the typical profile of horizontal reflectivity is the dashed line. So we expect a constant value of reflectivity below the bright bands, then a sudden increase, then a continuous decrease until the top of the clouds. So this is a chance to correct the data, and the correction is called VPR, vertical profile reflectivity correction. So this is in our region during the winter season is mandatory, because otherwise we had the information taken in ice, in snow, in crystals, but we want QPE with the temperature that below that close to the ground are above zero. And this is an actual vertical profile by Brick de la Croce, and this is the number of measurements on, and this is this is the freezing level. Oh, sorry, this is the number of measurements, and here you see the nose of bright bands, and then so it means that if your measurements at 5 kilometers, but your ground is here, you have to add almost 10 dBs to your measurements. This happens in stratiform precipitation. Then, if we put, I go back to the Italian weather radar network, and okay, this is our region, Brick de la Croce, and this is Lombardy. You see some data. Okay, you can put some information about the weather radar and its environment all together and define a quality index. So when you perform a composite between different weather radar, obviously you wish to take the best information from each radar. So a way to combine this is to build up, there are a lot of papers about this quality index. Obviously, the more simple are, if you consider the beam broadening, obviously between two radars it's preferable to get the measurements close to the radar instead of very far from the radar. So when you mix two radars, you can define a quality index that weight this geometrical feature. But other characteristics can be the distance, for example, the visibility map, like shown by Renz on AQPI. So you derive a visibility map that is the lowest beam altitude respect to the ground, and then you would prefer to take the lowest measurements respect to measurements aloft. So this quality index combine all this information. So beam broadening, the altitude of the beam, partial beam blocking, and so on. And another interesting way to get your quality, the quality of your data, you know that the spatial variability of the rainfall can be a lot. But if you accumulate over long time, you do not expect this. Yeah, for hydrology, semi-variogram is the magic word about correlation of between two rain gauges and uncertainty, spatial uncertainty. So on the right, you see the accumulated precipitation for the 1st April 2022. So it seems a huge period. It's more than 1 month, and hopefully in that time there was a huge amount, also a huge amount of rainfall. We had the flood. We had the flood in this region, as you can see by the numbers and the colors. But what is interesting is that you can clearly see some feature related to quality of your data. For example, here you see that we are not able to go beyond the Alps. Or here you see some partial beam blocking by Monte Crocione radar, that is in Tuscany, the region where Luca comes from. And then you see that there is no visibility, no chance of measurements in parts of the Alps. So this is another, and also you can see also some residual clutters. So if your data are contaminated by clutter, then you get either reflectivity. Then if you maybe that you are not able to recognize frame by frame, instant scan by scan. But if you accumulate, you can see even residual. And just to before talking about this, I want to. I do not restart, but yeah. Do you remember the usual radar equation? So the sensitivity of the radar depends on many parameters, but also by pulse width. And if you increase pulse width, what's happened in your mind? What do you think happens if I increase the pulse width? So if I double the pulse width, I can consider 0.5 microsecond and then move to 1 microsecond or at least 2 microseconds. Sorry, yes, shorter. Yeah, indeed, I increase. Yeah, in a way you're right. So we get more sensitivity, and if we double the pulse width, we gain 3 dB in terms of sensitivity. So, and here this is an actual example with the short pulse. This is a weather radar by civil aviation, C-band radar, and you see that yeah, we miss some signal here, for example. Look at here. Here there is a signal that here there is not. And also, yeah, we see that 0 dB. Yeah, also here you see some signal. You see also some interference here. But so in a cold weather, given that your observations are in the ice for most of the time, then it can be worth to increase the pulse width. On the other side, during the wintertime or I would say during stratiform precipitation, indeed the resolution is not really so critical. Yeah, because we expect a good correlation in the rainfall field. Oh, we discussed a lot about DSD and dropside distribution changing. I want to show you how it varies over our city. So we installed in Torino over the roof of ARPA Institute Thyssen distrometer, and those are on the left, this is the daily A value for the, oh, you remember the relationship, and then this is the current 300s, and 1.5 are the operational coefficient in the to convert reflectivity to rainfall intensity. And this is what the discriminator measure estimated during the day, during 1 day, 24 hours, and its variability within the day that is given by the Bloch's plot. You see that B coefficient do not change too much, but here values are changing, and they can also change a lot when we move to the convective season. Now we are starting convective season in Italy, so they are changing. So when you get statical precipitation, you get lowest value in A. When you have convective precipitation, you get highest value in A. And then if we compare rain gauges, this is a huge topic. How to compare weather radars and rain gauges. First of all, I would say the comparison must be fair. So it means that, if we want to assess our data quality, and we compare a rain gauge that is 180 kilometers far from the radar, and then the first observation is 8 kilometers above the radar, above the rain gauge. There is not much chance. So for this reason, this is our operational assessment between weather radar. So we make an operationally comparison over 24 hours, and we compare weather radar and rain gauges within 35 kilometers, and only rain gauges with good visibility. And only rain gauges that are in the proper location. So I made a study with Lombardy with their rain gauges, and when we compare weather radar and rain gauges, the correlation was almost zero. So I went to see the rain gauges. The rain gauges was a non-standard rain gauges, so it means that the diameter was such as this, and it was located close to a wall. So this is a non-standard measurement. So it measures something, but for sure it doesn't measure it. Or sometimes it measures it. So this comparison is unfair. So that's what it. So that's so we consider the rain gauge comparison over 24 hours, and this is done for the last 30 days. So to get the idea of how the weather radar is working. This is for Bricche della Croce, and this is for Monte Sette Pari. So Bricche della Croce is on the top of the hill, 770 meters above sea level. The other is 1,400 meters above sea level. You see that the correlation is less in this case. Nevertheless, we are during the winter season, so there is snow, and we derive the QPE from ice measurements, and then we get some underestimation for both the data. And those data those are the most recent, the green white, and also this radar are coming from the most recent days, and then the things are improving. So there is also a seasonal. We will see there is also a seasonal behavior in the QPE, and if we, as mentioned by Renzo, we made this comparison for long time, because the single day is sometimes it's quite hard to understand, but it's good for a case. But as hydrology says, do these things every day. And so as we are operational, we do this every day. And then you see that, okay, so this is in dB, so zero should be the ideal. And you see during winter season, some season, there are a seasonal So, and if we look, I got this case because, okay, there is a huge variability in the comparison. This is done comparing the QPE for 9 bins above the range. So we do not take 1 point, but we consider 9 bins and we take the median value to get statistics a little bit better. Okay. And you see this range is very strange, but it has a name that is the same name of the weather radar. So what this means is located in the same place of the weather radar. Then the comparison is unuseful. Yeah, because we have tier limiter, and so you cannot measure, you cannot estimate QPE properly close to the. So what's the sense of this story? Is that at the end, you must get the best observable, the best variable from your instruments. You can get the best. I'm not sure that we are the best in this, but you should get the best processing, but still some uncertainty remains. Yesterday, we discussed with the hydrologists about weather radar, rainfall fields, and so on. So in our operational, at the end of the story, there is a process that try to adjust the QPE with the rain gauges using kriging and making some real-time adjustment to get the QPE close to the rain gauge measure. And this is done by almost by all weather services in Europe. No, I'm sure, for example, Combi is the name of Swiss of the Swiss products. It is the same. It combines QPE. Obviously, you have to remove all errors and accuracy from the original measurements, but still some uncertainty resist.
This y-axis is the for from radar and gauge.
Okay, so this is the logarithm in dB between radar and rain gauge. And also this ratio depends on the accumulation time. We were discussing coming here with Luca. So this is the formula is log 10 of radar over rain gauge. But if you shorten the accumulation time, you get smaller numbers. And then given the ratio, it can become really an unstable number. So it means that you need to put some thresholds over these numbers. It means at least 1 millimeter for or 10 millimeters for radar and rain gauge to get a stable ratio. Yeah, otherwise it's not.
This number is acceptable.
Sorry?
This range is acceptable, but you got.
Yeah. Obviously, sometimes it's not. Yeah, like this. But yeah, regarding this, there are other stuff. For example, we use this ratio to locate some anomalous rain gauges because we have two trouble on rain gauges. One you never have here is the snow. Yeah, when you get snow, how much rain do you? How much rainfall do you measure on a non-heated rain gauge? 0. So it's snowing, then solid precipitation, then you didn't get it.
We got the same number. Even yesterday we were discussing with
Dr. Luca also, he also said absolutely right. Whatever you are getting, we also got, and he shared his paper also. So that's why I'm saying, because we are not confident so much of less and other thing. That's why I asked.
Yeah. So
That's the thing.
yeah. And the set of stuff for us are a leaf. After the winter season, some of them can block it by leaf because during the winter time So this some of them were not used because they were not heated, and so there was not just and also the wind is another. But were able during this job, and the recent case was this famous rain gauge in Lombardia, but there was other gauges where the correlation was so and the bias was so high that I discovered that this rain gauge was working properly. So this is also a valid tool to validate rain gauges, I think. And I would say that another recommendation from my experience, it's useful also to use intelligence, artificial intelligence. But before, I think a quality check is needed because otherwise you merge things that are not. Oh, what time is it? I will skip this, but okay, the chart was, if you look at this picture, you can see some features that are not related to the weather signal. So those are being blockage, bright bands. So, and so this is another recommendation that look at when we try to move from observation to QPE, we need to look at the single, even the single scan, if we are analyzing a case study, because you have to understand what are you measuring and what your radar is seeing. Yeah, we skip this, but this is Montesettebani polarimetric variable, and this is the full the uncorrected reflectivity. So it means that inside here there is also clutter, and you can see by ZDR, texture, or ROHV are useful variable to locate a non-weather signal from this map. No, sorry. And this is the clear. This is the clear map, and this is the particle ID. So the classification of hydrometers, and then you see this. This comes from 2nd April, so a few days ago. Okay, and this is means dry snow, and this means ice crystals. So this means that the first available observation of this weather radar was in the ice. But in the lowlands, like in Torino, on 2nd April, we had rain. Rain with 4 or 5 degrees above zero, but rain. Yeah.
Do we have some standards at which we can compare the rain gauge data and the radar data? And should we compare the intensity of rainfall or the cumulative?
No, accumulating. Yeah, and you should start with, I think it's better to start with 24 hours than, because if the things don't work at 24 hours, there is no chance to.
And the other question was, do we apply some correction because the footprint of the rain gauge is very less and the footprint of the radar above the rain gauge is a very high area. Do we apply some aerial reduction factor corrections?
No, we do not. But the another message is that when you correct radar by rain gauge, you must be sure that your rain gauge is in a good place and is that this point measurements is representative of that area. So you have to pay attention to this. And then we talk about C-band, S-band. Why more radars? This is a case. So this is an expo. Do you know what is an expo? So this is World Exposition. On 2015, it was in Milan. And then we installed our mobile X-band radar in Milan. And what you see on the left is reflectivity for the same time on the right. On the left are our operational weather radar in C-band. So such measurement is related to the fact that why this measurement is not so defined as by the X-band radar. Is it related to the band? So those are C-band operational weather radar, and this is the X-band that was located here. Which is the reason of these differences? Is it the band? It's the range and the altitude of the first available elevation. Yeah. So that's the reason. So here the radar is closest to this storms. The distance from here to here is 25 kilometers. Okay, so we get very good high quality measurements and from below. Meanwhile, here we are looking aloft because the first available observation is aloft and the radar is far. The C-band radar is 140 kilometers far from this place. So that's the reason why we can think about synergic use of different weather radars located in the place. This is another chance. So years ago, we got the X-band radar here. This is almost 60 kilometers, and we were looking, the same thunderstorm, and you can get. There was a ZDR column that we met yesterday. This is the RHI scan from the X-band radar. You see a really nice picture. Here you see attenuation. And then if you want to take a picture, it's okay. Okay. And then we can see the difference between our C-band operation we discussed yesterday. This is not continuous because it's called the pseudo RHI, because it is a cut in the bonnet scan along the azimuth. It is made. There is another. So apart from the gaps, there is another drawbacks of pseudo scan. This pseudo RHI. Can you figure out? Is this asynchronous? Timing. Yeah. Typically, you see something different because it takes time. As we mentioned at the beginning, we start considering lowest speed, antenna speed for the lowest elevation, so slow and then faster. But it takes time. And our scan strategy takes 5 minutes, but it takes 3 minutes to go there. So that's for that reason. Sometimes you see some swirl in the propagation direction of the thunders because it passed time. Here you see the nice RHI. So I think I am almost in time. So the weather radar and environment and the setup means scan strategy, how many elevation, PRF, pulse width. We learned that all these factors can affect your data quality. So if you operate weather radars, you need to deeply know where the radar is, how is affected by the environment, for example, snow, mountains, anacrop. We didn't discuss, but I think you are close to the sea, it could happen. And also how your data are acquired. The number of samples can affect your data quality. But data quality, nevertheless, is mandatory if we want to move to QPE. if we want to move to a quantitative use of the weather radar, for example, in hydrological. So obviously, regular maintenance is mandatory. So regular maintenance means that you stop the radar for 1 to 3 to 2 days and take measurements. But we have seen also that from operational scan, you can get some insight about the stability of your system, especially over long term. And also we have seen comparison with ground measurements is not really straightforward. The recommendation is to make a fair comparison and also to be suspicious even of the ground truth, because sometimes rain gauges may get some problems. I have a small story about a rain gauge in Torino. There was an hailstorm, and this rain gauge measured a huge amount of precipitation. Our rain gauge is a tipping jacket. Could you explain what's happened? Do you know how a tipping bucket rain gauge works? So there are small tanks, and then when a tank is full, it empty, and then click, and this is the minimum measurements of rainfall. The number of flip in the unit of time are proportional to the rainfall intensity. So when one is a tank or a small spoon, when the spoon is full of water, then flip, then the other, and so on. So our rain gauge was hit by hail. What's happened? Hitting the air, it make the rain gauge do these movements, and then it start to flip without rainfall inside. So it measure a huge amount of rainfall. But it was clearly a mistake. So that's all. If you have a question, thank you. Thank you.
I have one question, sir. That radar constant will be derived from wet radom and dry radom calibrations. Which one will keep for operations?
We use a fixed number. Yeah, we use a constant that derived from the very first calibration. Yeah, this is a good point because as mentioned by Elaine, so yeah, when the time passing, the coating degrades and the ability of the radon to avoid the film, water films degrades, and so you can get worse. There is another effect of radoms. When you have heavy precipitation and strong winds, you have a part of the radon that is dry and the other part that is covered by this water film. So this is an issue in the measurements. But first of all is to recognize that you have a problem. Then
Sir, when we compare the rainfall from rain gauge as well as from the radar, so we are talking about the credibility of the rain gauge observation also. So like yesterday, they were talking about to place 3 rain gauges and we collocated and at least 2 should match. So now the alternative is that can we do something like instead of putting 3 rain gauges, so 1 rain gauges and a JWD or a video distributor, and if all of them are showing the good correlation, can that be it's okay, it's a good sign, or I mean, instead of using the 3 rain gauges?
yeah, it's a very, very good point because I forgot to give you. In my idea, 1 radar and at least 1 distributor close to the radar. That's because close to the radar means far enough to avoid the TR limiter, so the blind zone close to the radar. So for our cases in Piemonte, our distributor is 6 kilometers far from the radar, And then from from the exercise that we made yesterday, or yesterday before, yesterday, that we made yesterday, we can derive the expected reflectivity, and then we can compare whether radar reflectivity with this parameter. So yes, I would suggest to have DSD measurements in situ coupled or close to the weather radar to use it for calibration. We do it. And now, apart from laser discriminator, there is also MRR, another discriminator. So another chance is to install such instruments, MRR, yeah, for vertical point.
So, yeah. Removing too much of clusters and beam blockage may cause underestimation in QP. And how to deal with it?
First of all, ground crater must be avoided. Must be avoided at all. Because I recognize it even in our long-term QPE accumulation, some spots that are related to some residual cluster, because it affects your data. And if you consider, if you get 30 dBz from weather signal, but at 10 dBz from ground cluster, you get 40 dBz. And if you remember the law, it means a lot of rain. So that's the problem. About partial beam blockage, you have two strategies. One is to recognize and to avoid these measurements. I don't remember. I can go back. Yeah, for example, here you can consider this. So the total here the total beam blockage is this dark color. But if you look at the lighter color, means partial beam blockage. So as I mentioned, there are two strategies. One is to avoid even partial beam blockage beams and move to the following elevation. The problem is that you are rising up and then you get measurement maybe in the snow or in dry band. Or the other chance is from theoretical calculation is to estimate the effect of partial beam blockage and add to the reflectivity. So that is another chance. We made a long-term comparison between rain gauges and weather radar QPE, and in our region, I told you it's a relative cold region respect to India. Obviously, for us was the limiting for QPE was 4 kilometers. So we say that we can see signal even above, but we believe that our QPE is not reliable enough if the measurement comes above 4 kilometers.
Hello, sir. So my question is related to something else. It's not rainfall estimation. So we do infer radar reflectivity height to lightning. Okay. So height is here more important for us. Maybe we are using 35 dBz height or maybe 20 dBz height. So sometimes we are keeping all the other like parameter or condition constant. So we find some ambiguity in the 20 dBz height. Like we are using 20 dBz height. Using some relationship, maybe the FIPO relationship is there. So we calculate the flash rate. So sometimes it's giving like keeping all other conditions same, but we are getting like a higher 20 dBz height. So it may be some methodological issue or maybe some measurement issue. So here, what kind of criteria we should follow?
Oh, this is really challenging research topics. So reflectivity. Oh. What we know about lightning is that those are related to high space. So I would suggest to investigate ZDR columns because those are related to strong updraft and particle sorting. So because we know that lightnings comes from particle sorting inside cumulus nimbus clouds, and so that could be for sure. You expect to having cloud phase, maybe Graupel also. So another chance is if you have a good polarimetric measurements, you could start from also from particle ID classification and locate Graupel areas and so on, and try to make timing. I would first of all, I would start to investigate how much delay there is from first signature, like ZDR columns or particle ID, and the first lightnings. I would investigate that. Then I will try to move to flash rate, but it's it's another topic.
We observed over maybe the France region, they are also using the maybe the single pole radar also, and they are giving the lightning indication through that height of that particular reflectivity. So same type of thing we are trying to do using the single pole radar, but we are facing this kind of ambiguity.
Yeah, we can discuss later. I'm curious about the paper of Meteor France about this. For sure, you get. I would expect only on the reflectivity. I would expect high reflectivity enough to having flash rate. But yeah, we can see the paper, and I think I believe that single horizontal reflectivity is not really enough to investigate flash rate. So you need more observable, because it's involved by microphysics, so particle types in the clouds. Also.
The question. So when comparing the rain gauge rainfall values and the rainfall values which are estimated from radar, is there a minimum value like above threshold above which we should start comparing?
Yeah, in our algorithm we use over 24-hour 1 millimeter, at least 1 millimeter for both from rain gauge
and it's recorded in both the rain gauge as well as the radar. Then only we should come.
Yeah, because otherwise the rates become unstable. Yeah, our minimum value of is 0.2. So our minimum, our sensitivity of rain gauge, so the tipping is 0.2.
So here we use 2.54.
Yeah, I think 1 or 2 or 5 millimeters. Yeah, to get reliable basis.
Yeah, Roberto, I have a few questions like radar usually gives rainfall. Whatever you use your radar, it will give some rainfall because this is a mathematical translation of power to reflectivity. And then you will get compare with the rain gauges, and it will match or not match. That is there. And now what is happening? People try to do some kind of like merge product, like they use satellite and they use radar and they use the rain gauges. So in that, what is happening? Mostly they use rain gauges, and then because your radar is not matching, and then extrapolation, interpolation, kind of the things, and they will come up with a good graph like 0.6 to 0.8 or maybe something 0.9. So I just want your recommendation whether we should do or not. And with AIML, I think they will get 0.99 also. There is no doubt about it. So what will be your recommendation? Means what kind of the things we should do first in terms of the data quality, radar data quality. Otherwise, these are all magical numbers and it will come. So it will be good if you can tell, like by your experience, like.
So thank you. It's very a huge question, but So from the cultural point of view, hydrologists believe in engagement for historical reasons. When could you avoid weather radars? Why the rain gauge work? Why the rain gauges work? So or the question could be when rain gauges miss, when we have convective precipitation. So if you have from the hydrologist I will explain a little bit better this after. But in our office in Italy, we have an organization where hydrologists, meteorologists, and geologists and snow avalanche stay in the same department. So we collaborate strictly with them. And so when you have stratiform precipitation over a long time, the rain gauge are representative of the rainfall fields because there is no special variability. But when you have convection and when you have small basins, when the spatial scales of interest, like the case shown yesterday by hydrologists, in this case, other observations are mandatory. There is no chance to reconstruct an event for this case. If I interpret correctly what Chandra had in mind is that it's not a matter of technician to put it together. Really, you need to collaborate because we need to understand requirements and also requirements from we need knowledge from other instruments. I see a lot of time comparison between radar and rain gauges, and then people say, "Oh, it doesn't match," and then I discovered that the radar was over for 6 hours. Then is not a comparison; it's a mistake. So my recommendation is that to build up a community that build up products for different users and that knows exactly which are the requirements. For example, if you move to urban hydrology, you need the observation more frequent than 5 minutes, even 2 minutes and a half or 2 minutes. But if you move to the yesterday case, 1 kilometer could be enough. For example, for that basin is almost like us, and the response time is another matter. So the calling the beginning data quality depends on user requirements indeed, and so you need to get range. Another limitation of the language is the latency time. I don't know here, but okay, in the past in Italy, when I started working, we got all engaged. We handled a network of 400 engages, and it took almost 1 hour to collect all the data. So we saw the engage, the rainfall intensity 1 hour past. So that's if we think about early warnings. No. And also the weather radar or satellite can provide the spatial distribution of rainfalls, and also it provides the opportunity to apply nowcasting methods, and you can gain in advance 1 hour lead time, for example. I hope I get your point. So
Means I understood because this is for the wider audience. Like people thinks like GPM means radar give that rainfall. I think some in the morning whether you are compare GPM rainfall and that thing. So this point has to be made clear before we make some comparison and like that way, because you can make two things compare, and if it is not matching and we try to.
No, I believe that when you make a comparison, you need knowledge on both instruments or both sources of data, I would say, because otherwise, you cannot interpret it. So that's indeed I was a little bit scary about the rainfall fields reconstruction by yesterday by artificial by machine learning, because I would start before with some traditional comparison to see what's happened, because where you haven't seen there is no chance to do anything. So I will start from these steps to understand better the environment, the instruments, and then eventually you move to machine learning.
Any other questions? Let's thank our speaker, Dr. Roberto Cameri. We'll break for lunch and get back at 2:30. Thank you.
Let's see. Can you see this?
Yeah. Good afternoon, everyone. Hope you had a good lunch. For this section, we have Dr. Devjyoti Datta with us, who will be giving a talk on challenges and advances in radar data assimilation for severe weather forecasting.
Amit, am I audible? Good afternoon, everyone. So I will be talking on the challenges and advances in radar data assimilation for severe storm forecasting. So definition, introduction will be definition of radar data assimilation. Radar data assimilation involves incorporating radar observations, reflectivity, radial velocity into numerical models, and its models to improve the accuracy of the forecast. This process helps to better represent initial conditions which is crucial for severe weather events. The importance of radar data assimilation in severe weather forecasting. Radar data assimilation is essentially in forecasting severe weather phenomena such as thunderstorm, tropical cyclones. And by incorporating radar data into real time into the model, these methodologies can enhance the prediction in lead time. And brief overview of the challenges and advances. While radar data significantly improves the quality of the forecast, it faces many challenges: that data quality issues, comparison limitations, model uncertainties. However, recent development in ensemble common filter, for data assimilation, hybrid data assimilation, machine learning, and so on high performing computing has enhanced the radar data assimilation capabilities. So, what is radar data assimilation? So, that initially that is to understand the radar data. That is what is radar, what it is observed, data coverage, resolution of from a single radar observation error, radar data quality control. And second is the radar observation operator, which will convert from a model variable to a observation variables. And thirdly, data is reflectivity data assimilation, and then the impact on the forecast. So radar parameter, these are the radar parameters, reflectivity, radiality, spectrum. But radial wind, we initially it is assimilating a radial wind. It is easier that it's and second reflectivity. Deriving it to reflectivity to rain rate and through LX and later heat nudgings assimilations, and another is a direct assimilation or reflectivity. So what are the challenges? This data quality issues, that clutter, attenuation, weight rhythm, anomalous propagation, radar coverage, gaps, resolutions and limitations, uneven spatial coverage, especially in rural mountainous areas, beam broadening at greater distances, varies by region, seasons, storm type, velocity de-aliasing, and uncertainty computations and latency issues. Quality quality index, instead of directly putting into the data, we need to quality control the data. Quality control is basically in what we are doing. We are not removing the raw data we are putting a quality index to identify which one is bad data and which is good data. Based on the quality index, its decision is taking this data will go to the system or no. So quality index schemes are, these are the is employed to evaluate the radar quality. Quality factors, the quantities have impact on the weather data based on data quality. Quality functions, that formulas for transformation of each individual's quality factor into the relevant quality index. That quality indices quantities that express the quality of data in terms of a specific quality factors and weights of each of the individual QIs. And finally, quality index will be quantity that represent the quality of the data. Those are the general formulations, minimum value, then the additive scheme and multiplicative scheme. Here in NCMWF, we are using additive scheme. And there is a simple image where that the around Patiala, where blockage is vicinity in the radar, that QI due to sending beam blocking, reflectivity, attenuation of the reflectivity engine, and QI of attenuation factor, average QI due to all the effects. Coming to the what is data assimilation? Data assimilation is a means numerical prediction in the initial value problems. But why you require that if initial condition we need for to running a model, we need an initial condition, then lateral boundary conditions, lateral boundary conditions and surface conditions. To get an accurate estimate of the initial conditions, we need as dependence on the initial conditions. If we get more accurate initial, we'll get a better forecast. Data is the process where combining observations and from a background sort forecast to get initial conditions for the NWP. The purpose of data is to determine as accurately as possible to state of the atmosphere flow by using all available information for NWP. So advances in data assimilation techniques. These are the data assimilation techniques which radar data can give additional benefits. Advances, ensemble Kalman filters. The ensemble Kalman filter is the extension of Kalman filter that uses set of ensemble simulations to estimate the forecast error covariances. It works well for large nonlinear systems and is widely used in meteorology and oceanography due to computational and efficiency and adaptability. 4D is a four-dimensional variational assimilation. 4D observations over a time window by minimizing a host function that includes both model and observation errors. It uses an adjoint of the model to estimate compute gradients, making it suitable for high resolution systems, though it can be computationally intensive. Hybrid model methods combines the strength of ensemble, Kalman Pinker, and variational approaches like 3-bar, 4-bar. They leverage the flow-dependent error covariance from ensembles and the optimization framework from variational methods, improving accuracy and stability. The particle filter is a process which is used nonlinear, fully nonlinear, where non-Gaussian method is represent the posterior distributions with a set of weighted particles. It avoids the linear Gaussian assumptions of Kalman filter, but suffers from the curse of dimensionality in large systems unless modified for localization. Machine learning integrated data approaches. This recent approaches incorporate machine learning methods to incorporate parts of the assimilation system, such as emulating error statistics or surrogate models. This hybridization can improve and speed the performance, and especially when models are expensive to run. In NCMWF, we are using variational methods for data estimation. In regional, we are using 4-dimensional variational methods, and in global models, this is a hybrid method using where ensemble and combination of ensemble and variational that co-differ. So that variational method, that Jx is the cost function of the analysis, and where xb is the background state of and x is the true state of model state, and h is the operator, which is this hx is the observation operator, which is bringing from model to your to observation space. Y is the observations, and B is the covariance of matrix of observations backgrounds, and R is the covariance variance of observations. So the, minimizing this ZB and Z0 that will get the that minimizing, ultimately minimizing the cost function Z. So background is the this is initially what to do minimization. Initially, this background is we start with the considering the background is this two state. Initially, x is equal to xb. Analyze implement is the x minus xb. So background error covariance is the variance in the background. This is the there will be in the background consists variance, the background quality, and the correlations. That correlations is the quality horizontal and vertical relations between the two analysis points, and is balance is the relation between two analysis variables. What are the steps using in the observations? So this is the background of which is first step, which is background of is the same for all observations. So so this first step is the understanding the observations. Why this is name variable observe geographic and time distribution, space and time resolutions, observations errors, quality control and bias correction, acceptable format. Second step is to build observation operator to link the variable x to observations hx. Conventional observation, there is a Sonde surface. These observations require only 3D interpolations. Non-conventional observations, these are required complex function like reflectivity, which is a function of mixing ratio of rain, mixing ratio of cloud, then hail, ice. So radar radial wind is a function of UV and W. third is the definition of observation error variance. That these are the at NCMWF. These are the models which are running at NCMWF. And this is the 4 kilometer regional model, which is giving 72 hour forecast where which I'm talking on, and there is here we are assimilating radar data. And this is the model configurations used at NCMWF, and this domain which is be used. This is the regional data assimilation systems at NCMWF. So that's what it will do. Yes. From a, you need a analysis, you need a background forecast from the previous cycle. That that will go to the OPS systems. This OPS observation processing systems will see the body set, then it will compare with your our forecast background forecast. That is O minus B, and it will see the consistency test and consistency of the data, then location. And after once this OPS will check this data, it will pack data will be go to the this variation this part to the body part. Another this from the short forecast that this is the LS state, this is the linear state files which will go to the 4D systems. And with that, this combination of these observations and the forecast, it will create an analysis increment. Analysis increment along with this short forecast, it is not adding this analysis increment directly to the forecast to short forecast as because if we directly add it may got a shock. So instead of that, this with IAU mean incremental update is used to create the final analysis. This is the IMD radar network which we are receiving in real time. And in that radar networks at present, we are assimilating only SNC band radars. And for a particular day, this during the monsoon period, these are the assimilation number of observations which are assimilated into the system for each radar for both reflectivity and radial velocity. Whatever we see that very less number of observations is getting into the assimilated and maybe around 5-10%. And quality this OPS these observations which is going to the OPS will reject also will do some additional quality controls like it will be rejecting observations which is less than 3 degrees Celsius because to avoid the bright band effect. Another after that those observations will create a super observations instead of assimilating directly because this may create if we do directly assimilation with the observations with thinning, you may lose informations. Instead of doing that, go using a super observations and with Poisson thinning. Super observations are calculated with 9 by 9 kilometers and thinning where it is using 9 kilometers thinning. So then coming to the radial velocity operator. Radial velocity operator, what it is doing, it is converting this model wind to radial wind, and in that what NCMWF system is doing, we are not updating this W. W is taking from the background file from the initial value, from the initial value, that is from the background file only. Only updating this U and P. Super observations. How we are creating the super observations? This simple horizontal averaging of the observations can reduce the fundamental disparity between observations and the models. Also, it may lead to loss of methodological information. To avoid this loss of information, a super observations can be created by averaging innovations. So for a particular day, means this is the raw wind and this is the O minus B, and this observation, super observations are created means using this O minus B, and for this, these are the radars where this number of observations are getting into the model. So if you see here with the analysis increments when we are assimilating the radial wind, this shows that over the peninsular India, this wind is getting it increased the wind speed of the over this peninsular India, which shows that because of that there is a low pressure system is there, and this it's with the assimilations are treated that increases the speed of the wind, and we notice that RMSE of the O minus B before and after analysis O minus A is reduced. Yes. Yes.
So when you say number of observations assimilated,
yes, yes.
The radius knots.
Yes.
Maybe 25.
Yes.
Whereas radar can have a lot of.
Yes, yes.
A number of.
Yes.
One radar you may have a lot of observations.
No, that's what I am telling. From one radar, you may have lots of observations, but all the observations are not getting into the system.
What fraction is getting?
That's only I told that it is around 5 to 10, not more than, because and one problem is there. When we are creating this super observations, because directly we are not assimilating it, because if there will be correlations will be there between these observations, the dimensions would consider that there won't be any correlation between these 2 points. So when uncorrelated observations. So when it is coming to that, for that, this super observations we will use it, and super observations it will consider inside the super observations. It should have some observations, like we consider if it is above 3, above 2, then only this this grid point is considered to make a super observations. So and
how do you qualify that super observation?
Super observation, this is the one. Super observation is like a background. One is a background. Here you see this. Why is this? Why is the super observations? For XB is the background. So background and your observations. So it is actually it is innovations. It averaging the innovations, not directly observations is. So here this Y is the your observations, X is this your background is converting to your observation space, and then it is for that Y naught is the resulting super observations. Because to that reduce the that correlations between these two tests. And if we do the super observations, that if we do a thinning, directly thinning, it will lose the information because it's just averaging. But if you do a super observation, it will remain that observations impact on that. So this event where radial wind has assimilated, and we saw it during the monsoon time over this region. our decision has the impact of this simulation of this radar multiple radar. Also, but one thing is that this assimilations is only the short scale. It's not giving impact in the larger scale. I mean, more than one day, it is not having any impact. It has impact, but very less amount. Secondly, we started assimilating reflectivity. Directly assimilating is a tough to construct that observation operator and is. So initially we started with the assimilating it with the converting it to a range rate and then assimilating. What here we do, we consider that range in a when observation has a rainfall over that, we see that whether model has a rain over that, we threshold at 0.1 mm per hour. If it is not there, model has if it is there, we directly reduce that. We'll directly modify that. That latent profile. We will scale the profile, and if suppose if it is not in that point, it is not there, then we use a search algorithm of 16 points we consider near to the point, grid point, and if there is any point has some rainfall in the model, then we scale it. That election we also can scale it, but with a reduced. But if there is a model has not rainfall in all the 16 grid points, and if radar has rainfall, then we rejected that observation. And elections also has impact. It has also skills, and we have seen for a case over Chennai where this coastal rainfall, that near coast that rainfall over the near coast that. Bay of Bengal rainfall. This rainfall is missing in the control experiment, which after election this rainfall has recovered. But here main problems are there. This is data equations, rainfall, observation, rainfall. Better rainfall. Error in the rainfall, and those is a problem. So for that, we started assimilating directly reflectivity. Reflectivity model has that observation operator for reflectivity is radar for rain and ZH for hail and snow, where these are the mixing ratio for rain, hail, snow. But at present, only we are considering only rain case. We are not. We are using these operators to see the evolutions, but we are not updating it in the assimilating it this hail and snow. Only in the rain case only we are assimilating. That is also below freezing levels. So what we see there, coming to this high resolution, it's whatever we are speaking that mostly it's a, and it will be that if we use a simulation cycle like hourly simulation cycles, then data can be used for every 10 minutes. Data can be used. So that, and this here, this is the diagram flow chart where this observations is coming up every 10 minutes observations, and forecast is every 10 minutes is taking that hourly, and that its analysis is creating for the next 1 hour. So it will be simple where this continuously is assimilating up to 6 hours, and we are giving a long forecast from that. And this 3 domains which we set, and in that 3 domains where we're running this high rapid refresh systems, and mostly it's 1.5 kilometers more. And we noticed that over this Mumbai, this with HRR, this rain fall which is coming above 64 is missing in the control. It's very small amount of the and its displacement is more in after assimilation. This displacement has corrected and rainfall also is increased, but that location still is not able to like what it observed. So how you will verify if this type of things are happens if there is a displacement in the systems, and it thought that it is required some verifications techniques. If I am talking on a continuous rain area method for spatial verifications. This is a spatial verification technique is used to assess the accuracy of quantitative precipitation forecast. Focuses on verifying forecast by identifying and analyzing rainfall features like contiguous regions with rainfall above a threshold rather than a point-wise comparisons. To why CRA reduces penalty for small spatial shifts, more meaningful for convective mesoscale systems, and offer insight into displacement, volume, and intensity errors. CRA method steps defined a threshold to extract continuous rain area from forecast and observed fields, match forecast and observed rain features, allowing for spatial shifts. The compute the error, the total error and displacement error is a decomposition into the different component is expressed as MSC total, MSC displacement as volume plus MSC pattern. Displacement error is the distance between the forecast and observed rain area. And volume error is the difference between the total precipitation amount pattern is the pattern error. There is a structural mismatch between the alignment. What are the benefits? Separate different sources of errors. Enables feature space verifications. Useful for high resolution model and convective precipitation effects. This is a case which with radar data estimation we see that these are this. What we notice is that displacement matters. It has a correction in the displacement error and the intensity, and in displacement and the intensity, and it improves the RMSE and the correlations. But still, why some weather forecast sometimes wrong. Forecast skill increases not only by increasing model resolution, but also by improving the model numerical models and the method of solutions. Even if we have a perfect forecast model, we would not be able to predict the state of the atmosphere accurately by long-lived periods, because nonlinear dynamical systems that describe the atmospheric behavior are sensitive to small changes in initial conditions. A chaotic behavior occurs and leads to an unpredictable long-term evolutions. When solving deterministic nonlinear dynamical systems that exhibit sensitivity to ICs and initial conditions. Future direction and emerging trends. Assimilation of phase array radars, and polarimetric radars. Integration of high resolution fast update radar system like phase array, better exploration of polarimetric variable differential reflectivity specific differential phase to retrieve microphysical properties, rain, hail, size distributions in the data assimilation systems. Improve microphysical schemes, coupling radar data assimilation with more realistic and complex count microphysics, assimilation of radar data and microphysical parameters like hydrometer mixing ratios for better precipitation forecast and storm structure reconstruction. Ensemble-based techniques, use of ensemble, Kalman filter, and hybrid ENKF variational methods developed to development of techniques to handle high density radar observations and improve storm scale forecast. High resolution model, increasing model resolution to capture convective process without parameterization with real-time data assimilation with high resolution model to improve nowcasting and short-term severe weather for predictions. Assimilation of radar data in coupled models, or use of nested or coupled models to represent the interaction between the atmosphere, land, and ocean, incorporate radar data into across scale domain to improve the integrated large integrated Earth system forecastings and a machine learning and AI integration. AI ML being used to enhance the radar data assimilation schemes. Conclusions: radar data assimilation is essential for improving weather forecast accuracy, especially for high impact events like severe weather events, rain, or thunderstorms. Advanced assimilation techniques includes ensemble-based methods, variational approaches, hybrid system. These techniques are significantly enhance the use of radar reflectivity and radial velocity data. And emerging radar technologies such as dual phase radars offer more detailed atmospheric information. Innovations in machine learning and high performance computing are driving further improvements in forecast accuracy and lead times. Ongoing research and development are crucial for enhancing the real-time predictions and reducing the social impact of weather events. I'll show some. It will be difficult for me to run the system, but disconnect is get disconnected. But I'll try to show how the structure of the systems and how it's running. As what will do that whatever data is coming from the IMD, that will be packed into the into a grid format for to assimilate into the data. So these are the scripts which is using.
All the volume data, you are taking it any particular.
We are using all volumes, but means we are assimilating up to all elevation scale, up to 10 elevation scale. But when we are assimilating, we are restricted to height in the when it comes to reflectivity assimilations. Height we are not assimilating above freezing levels, because that is a problem with this. To get the that microphysics is to convert it to that from the mixing to equivalent reflectivity, ice reflectivity, and only in the warm rain case. When warm rain means below freezing level.
There are two scans in IMD, MDB and MDC something, right? So lower elevation angles, there is a 3 angles only. Another one is some 11 angles, right? There is a 2 sets of.
There are 2 sets of. One is 3 elevation scale, and another is a 10 elevation. Only we consider only 10 elevations, because 3 elevations one problem is there. That is it is a long range they are using. Long range when it's a QP actually. QP. Yeah. Because of that only we are not that considering. We are only considering this 10 elevation scales only.
So you use only the reflectivity and this one.
When ready.
When it comes to 2 different radars or 2 different specifications, how you are taking it?
Which one?
2 different radars.
Yes.
Different frequency.
Yes. No, that at present this whatever we develop, it is developed. It was developed with respect to S and C band. Okay. X band is still not developed. So X band still we are not assimilating X band. Only in the C and S band. Thank you. So this way, this radars will mean it is it's taken from the radars and data, and it's taking into the systems. I'm showing one. So this will create two files, one for the reflectivity and another for radial velocity. These are the apps, different apps which will take care of different processing observations. Then once this will process these observations, it will create this analysis file that are that UKB. Actually, this is we adopted this model from the UK Met Office. Because of that only, this is a UKB, this is UK variation, and this that will create this this analysis will be created. Here, these are the observations which is processed, but I will show here with the process which says radial wind and reflectivity. You are using the radial wind, check with the UV, not W. No W, only UV. Only UV. You are checking with the UV, other things. Yes, yes. Okay. W is always first, only you are using radial wind. Yes, yes. Only U and V is updated with the model. Not
are you getting the bad profiles or just radial wind or assimilation?
No, this is radial, not bad. Not bad. Bad is a bad. Actually, bad wind we initially tried. Bad is it's like a Sunday only, it can be simulated. But problem with that bad has this observation error. Okay. This is an observation error, because when it's a product, it's a product, when it is there, that it's difficult to assign the error, observation error. So if we do not know the observation error, then it won't give that impact.
But how do you get the UV without bad?
No. That's only model wind is converting to radial.
Okay.
Yes. Yes.
Okay, so you are
ultimately it is updating this U and P.
Okay. And that is also reason for limited observation, because it's not consistent with the
yes. Yes. Yes.
Continuous the project next head. You are doing this basic just observations, right?
Yes, yes.
And what to do with that?
Yes, even in case of reflectivity, also we consider in the polar coordinate. Actually,
right.
Not converting it to a Cartesian.
But somewhere you mentioned is a gridded data.
No, we do not take a grid. Grid will be the model is creating the grid.
Okay.
It's not.
So after the coordinates you are getting.
Only we are giving a flag to the data. Suppose if we know prior flag, if we know this observation has a quality is bad or this, then we are putting a flag to that. So the assimilation system won't take that data, particular data. Still some error maybe that is again assimilation systems with background check it will remove.
Typical models, they use the standard deviation things will play an important role.
Yeah.
So why don't you use the velocity variant, that is the spectral width, the third parameter, second movement?
No, spectrum width can be used for the quality control.
Correct. Are you using that?
In creation of quality index, we are using for radial wind.
Oh, checking gradient.
Not.
That's good. That's the wind, and this is the variance.
Yes.
To expand.
Yes. We have a plan to include expand and to expand also, and we want to use this ice phase one and then hail also. But at present, microphysics, this model microphysics is not capable of handling this ice and this hail one. So because of that only, we are still sticks on that rail.
But you have any slide radar data assimilation quantity this much percentage to achieve that?
Yes, yes, yeah, I showed many, but exactly here I didn't put that how much percentage it is there. Percentage, if we see, it will be around 10 to 15.
So you mentioned
Here and here.
one day podcast.
And yeah, I'll show you in a, this is here. This is showing some better way. So this month's RMSE has reduced. So it will be. It will make it big. Full screen. Full screen. Okay. So these are this is the error in it is reduced from if you say in the displacement, it will reduce from 14 to 7. The displacement it's improved the displacement.
Volume error.
Yeah, volume yes. That is the volume means the intensity. Actually, main problem is that increase the rainfall. Because of that only it is coming. Actually, with putting this radar data, this rainfall has increased. So a control is showing less rainfall, but one it is better. I mean, because not showing in a rainfall, if it is showing more rainfall also, it is a better and under prediction than better than under prediction. So because of that only that it is not showing any improvement in the whole.
Do you think whether it is extent of draw more higher because of the
Observation is like 18.6 earlier, and then with radar data assimilation, you are getting like 25.5. You know the first figure from my right.
Which one? This
Yeah, first figure.
first figure.
The bottom one you mentioned rain volume.
Rain volume.
Yeah.
Yes. That area you see rain means there's actually this volume is it is not considering vertical. Okay. Volume in the sense means intensity wise. Means how much area this rainfall is there.
Because intensity wise, you are getting very close, like 45.6, and it is like 44.4.
Yes, yes.
But volume wise,
Volume is more voluminous. I seen this. If you see that, if you see this in the, you see in the that mainly that West Bengal, no? West Bengal area, where their rainfalls are not there, but the observation has rainfall. But here you see in the when water assimilation, you see this area, this rainfall has come. Though this maximum rainfall is not able to capture, but this over the area, this rainfall has increased.
Yeah, I was not there, maybe I guess. Like you consider like 20 mm per day threshold.
Yes, yes.
So that means what if your rainfall should be always greater than 20, right?
No, that only that rainfall
Those
only
areas.
considers. Those areas, not in that other area. Because when you are doing a CRA, you will consider a threshold. With that threshold, how much area is covered? You need a threshold.
20 mm is a big number.
No, that's only we want to see heavy rainfall, not in the lower rainfall. Because low rainfall already this control is predicting. But in case of in case of severe events, after assimilating, whether this heavy rainfall is heavy means not heavy, it's a medium to high rainfall is it's predicted or it's improved that prediction or no. Some other
temporal timestamp also you are.
No, I'll show some others even. So this is just so this. If you see a temporal scale, you'll see this during this initial time. No? This has a so DWR this rainfall is there and GPM rainfall. We see this that RDA that 1.5 kilometers rainfall, which it's matched with this with your radar. But the control is control. It's increased the rainfall during this initial periods up to. Here we see up to 12 hours. That after that, though it's not giving set.
It's a case to case, or you have the
No, this is a case to case. Only this here where we see for a longer period. This is average. Then only actually in case to case, in sometimes it's giving in day 1 forecast, but day 2 forecast it's not showing any impact. So we consider for a longer period during the monsoon period, and from 17 to 23 August, this whole spell, this is the onset, active monsoon period, another 18 to 24. Here we notice that day 1 and day 1 and day 2 has the improvement is there even day 2 also, some but very less.
So while you prepare the grid data for data assimilation, are you looking at each grid point have the pair available and reflectivity and velocity? Then only point
no, it's going separately. But once you are assimilating, that balance will consider the balance.
If reflectivity is qualified and radial velocity is not available or rejected, so still you go for. Can you consider that?
No, that will consider. That is a problem. It will consider, but one thing is that it will see the O minus B. O minus B is very large, then it will reject.
It's background. Which comes from the model. So you take model background as a reference.
Yes.
For a true ground observation.
Yes. But still has a issue. Means in the sometimes what happens when reflectivity is
that is a requirement of this setup, or why we take at O minus B.
No, O minus B. Actually, we believe in forecast.
Okay.
But we consider this is first guess is the best forecast
because that data is always available and the graded data. So you take that as a reference. Model background. That is a graded data, whereas your observations are scattered.
Oh yeah, that is also. Actually, main thing is that it is a graded. And one thing is, second thing is that we know the model error in 4 variances. So because of that only we trust this model forecast than the observations. Because we do not know observation has whether it is a good or bad. And that is if we are forcing it, then it will create unbalance, or sometimes this model will blow also. And some other issue also is there, like high reflectivity assimilation. That is a big issue is there, because model is predicting like 20 dBz where reflectivity is coming 40 dBz. So high reflectivity assimilation is a big problem, because innovations will become very high. At 5 kilometers we are restricting. Above we are not considering. Higher that we are in. We are restricting into 5 kilometers, and another also we are putting in the model that temperature, from temperatures also below 3 degrees Celsius. Zero is the bright band, but below 3 degrees Celsius we are removing the data. Means that data is not going to the system.
Again, you have to do because you say you want microphysics.
Those things is because that depends on the once this microphysics parameterization improves, then this can be in assimilations also. We can use those things, because main problems is that is the microphysics also.
Parameters. Because in continuation to this one, like you said, we are using model as a background. So there also you will consider like model microphysics as a background, or you
no microphysics, not rather microphysics, because when it is model, when you are considering this model model mixing ratios.
Okay.
That this is coming from where from rain is creating. This is microphysics is there, which is creating your model.
Okay.
Rain.
Parameter classifications.
No, it's not from your this one.
I also have another question. In one of your first slides, you showed the super observation.
Yes.
And can you go to the slide? Because I see that actually it looks like the window observations in that case. Yes, the top left row observations with the percent. Actually, the wind seems much lower than in the background because the observation.
Yeah.
So do you have any difficulty in assimilating this observation when the difference from the background is too large?
That's why
rejected.
Yeah, they get rejected. But we force it here 10 meter per second. If it is
tolerance is 10 meters, it's quite high.
Quite high.
And you don't have any problem.
Up to 10 meter it can assimilate. 10 meter per second. Because it always been we notice that always this difference is very high with this with the background. So in case of this radial wind, we put that one. But in reflectivity, this is a problem.
What is the pressure?
But reflectivity, what reflectivity, we put a threshold like actually we are not assimilating higher reflectivity above 50 dBs. 50 dBs. Another what we are doing, if it is coming to a higher reflectivity, innovation is high. We are putting a norm in that. Means it's a normalization, Haber norm you are using, so that it get though innovation is high, it will converse. At least it will converse. Otherwise, it is a very difficult to get the converse. Model is predicting suppose 20 dBz and where radar has having 40 dBz. Is say you need to these are in English files where you need to give this this will what method you will do that super ops will create and those. And this once this process this will process this app will process the radial wind. Similarly, reflectivity consider that observe the process that reflectivity on drift. After once this process will go, this analysis it will run for analysis increment. So var will run, and once var will run, it will create a analysis increment. So once analysis increment done, so it will add with this with your background forecast with this model. Then it will create an analysis for a long forecast using long. So this here you need to put the start date. Suppose we are inputting. I'm putting I'm putting today's date because the one problem is the data is to get it to migrated. Migrated means it is goes to tape. It is stay in the HPC for 3 days. So because of that, only because of limitations, I am not able to run in the older dates. Current date only. And here another thing is that here you need to mention your observations. So observation, these are the observations which are getting into the assimilated. And here this Doppler radar radial winds, this is the reflectivity, is along to other observation satellite. These are ATMS, these are different satellite sensors, along with your sonde surface data. So this command will so this way, this will run. So this actually this if it is running in real time, this will this brick will it will look into the system where the data observation data is there. If it is data is available, then only it will succeed. Otherwise, it will continuously it will monitor. So in this first model from a global this boundary is coming from the global forecast, and this global forecast, it's this create BC will create the boundary conditions for the modeling. And once this is created, this is created, and this will run. Your first is recon your that analysis, previous cycle analysis from the global models, because it's running is a cold start. Cold start means it's coming from the global. And once this one will run this, and then it go to you have a analysis and a forecast boundary conditions. It will run your short forecast. Once this short forecast will run, then once short forecast is completed, it will run for 6 hours. Once this is completed, then this observation processing will start. OPS will run. So observation processes, it will this way this all the observations will be processed one by one. These all observations will run in a series in a parallel with one nodes per observation. Right. Which one? Rather, these are ATMS. These are different sensors. In satellite sensors like ATMS, CRIS, the GMI, high, low, ISE. Satellite wind is a derived wind from the satellite motion spectrums. Another is a scat wind, is a scatterometer wind from satellite. And this severity is this is geostationary satellite sensor from the Meteosat. And sonde is our sonde, and surface then radial winds, reflectivity. AHC is a satellite sensor from Himamari. Himamari is a satellite from Japan. Once additional that here another that aircraft I have not included in this, but it is their aircraft is also getting tested. Aircraft passes are very less in for regional, but for a global it has very good impact. Global aircraft. Once this observation processing is completed, then our this R will run. This These variational systems will run, and this will create a analysis increment.
You find any helpful that ART radius on the data we are taking the core in a day, whether that is helping?
Radius only is the most impactful data.
Yeah, that's why I'm asking. In a day, instead of 2 profiles, we are giving you 4 from that one. And even
it will be good.
Even a written profile also we are giving. So is there any work happened for the better improvement?
Means at present I did not start with that, but whatever IMD, because operationally whatever we are receiving, that's only mainly I am using.
We are demanded to give all the profiles, even a written profile. We have given.
Okay, but maybe means Sunday people, other people are looking. Maybe they are trying it, but I do not know. Because I only using whatever IMD Sundays are there. That's fine. But Sunday is a very good data. If we get more frequent data, this has more impact because it is directly linked with the temperature. This viewing time. And it's a very better than any observations. Still, this after that, this one once this will complete, this will create a analysis increments. Once analysis increment is, then this that forecast will run along with the analysis increment and the previous background file. It will create a analysis, and for then that analysis can be used for long. So that I because it will take a long time to complete these things. So I'm showing in our operational area compared. So this is your analysis ATMNL file is the analysis increment. This ANL underscore INC is the analysis increment file, and ATMN ANL this is the analysis file which will use as a analysis for the initial condition for the long forecast. So and these are different data which are used in this. It is creating by this data intermediate data. Can I stop? Or because this finishing this model, it will take around one and a half hour. Questions?
You said your income model is running at 1.5 kilometer resolution. And while you are sending the data, you are putting as kilometer resolution.
That because that is the main thing is that we do not want we do mean correlated mean correlation between 2 points. Actually, data is considered uncorrelated. So to get to that uncorrelated, this means up to how much thinning will give a benefit. We need to do some experiments with that, how much thinning will give a benefit to the system. Sometimes it is not like that. If we are thinning in higher thinning, and it will give a higher impact. Sometimes even if we give sometimes if thinning to 15 kilometers, it may give more impact than thinning to 3 kilometers.
So it is the optimal.
Optim depends on that observations, and you need to do some continuously. You need to run and see the impact. Then only you can optimize how much it has having an impact on the systems.
about artifacts or, for example, ground collateral contamination. Would you prefer to have less eco-beat, less reflectivity from lesser weather signal, or a little more ground collateral? What is has the best, the worst impact?
Means if means that is a big problem. Means it's a big problem. Means that's clutters mainly partial big blocks, and we are trying to flag it with the using the orography. Orography, we are trying to flag it, which having a means if it has a mean that we are assigning QI for that. If it is having up to some threshold we are putting that, if it is crossing that, we are not taking that. We are not, it will rejecting actually wherever they pocket.
Would a quality index help you to select or to avoid some?
Yes. Quality, because directly raw data we are not touching. Only we are putting a quality index with that, whether it should go to the model or not. Depending on that, if it is having a good quality, then only it is going to the model. At present, we are doing. We are not considering which has having some errors. But beam broadening still we are not considering beam broadening.
Area you consider
100 kilometers. Because of that, only beam broadening still do not consider a bit more. It need to consider, but has some problems.
So that is for like 1 degree beam width, right?
Yes.
So if your beam width is coarser, so you will not use those data.
Those things we need to see.
Because why I ask is like from the morning we are in the sessions of the network of the radar. So their beam width will be because smaller antenna and for the thing like 2 degree beam width as I mentioned, like for Mumbai. So in that case, how you are going to
that only then we need to consider the beam broadening effect also. If we consider, then only this can be assimilated. Otherwise, it will give a wrong. It will have some.
So just wondering, like you said, like microphysics, whether like suppose in India we will have now more like if someone like K band radars and W band radar, and you derive this cloud microphysical properties like the other agencies do. That is going to help because you are using HEMA.
No. This will use because at present scenario it will use it will help in identifying the quality.
Yeah, like HEMA data, like Japanese. They give these microphysical properties.
No, we are not assimilating. We are assimilating directly raw radiances.
Oh,
no, not
the
radiance. And in IR, at present we are assimilating only clear sky, not cloudy pixels. IR. And only cloudy space scale are assimilated for microwave sensors like ATOS, microwave sounders.
Okay, thank you.
This is a general question to all the radar experts. I noticed that all the blue band radars they only point either upwards or if they are in a satellite, there's only one outside. It points directly downwards. There's no swath width or Why is that? Does it attenuate too fast or just why is that?
I'm sorry.
So like any radar, so the usual ground-based radar will have a scanning area.
Yes.
On a satellite, it will have a swatch. Yeah. But the cloud-sat radar, which is a W-band radar, 95 gigahertz, it just looks straight down.
Straight down, it's like over.
Yeah. No. And even ground-based W-band radar, they usually just point straight up. They have no swatch, zero swatch, just one propel. So why do they do this? Is it because of attenuation or something else?
That maybe that radar expert.
It's a different question.
Radar expert only can tell.
That is basically due to the gaseous attenuation. So, water vapor and oxygen you have to consider. So in general, like if you go higher and higher, like elevation, it can go up to the 25 dB. Okay, so it's not a good idea to do this scanning and other things. Vertically, it is very less. It is like less than 1 or 2 dB. But if it is like scanning, you can see up to 1 or 2 kilometers, but in Indian monsoon domain, it will be much.
So its profile width is about 1 kilometer, so it can see straight up. So I get that there is attenuation. I was just wondering why not at least a 5 kilometer, right?
That's what I'm saying. So gaseous absorptions and other things you have.
How does it scale? Can you I get that 25 dB is so at what angle would it be 25 dB? Straight down, it's
so if you consider like a 5-degree elevation and you want to see like 20 kilometer, so it will be like that. We have that model plot. I can show you.
Yes.
Madhu can also add.
And discuss that. It's a small, high frequency and smaller antenna. So vertical is more efficient. So instead of scanning things, you have to take the object more at the angle. You require a lot of range corrections. So that is one thing. Yes, no, high frequency vertical looking is better because you are making it statistic, but you can exactly get the complete micro sticks.
Also, if anyone has any idea when we'll be getting our own documented answer.
What was the question?
So you guys have any when by what time we'll be getting our own W-band radar next year?
Okay. We have a K-band radar. If you want that, you can take the data. It's available with us. Yeah. So W-band, if you want to get it, actually it's not good from surface. It's highly attenuated. So with the larger use of this better. But we are bringing the both dual wavelength radar that Pandis are showed in the first year. So dual wavelength radar first time we are trying for this because the differential specific differential things will come to two wavelengths. It's a better for the ice physics for monsoon. That's what is the aim of this dual wavelength radar we are bringing.
So
there W-band will be there.
So okay, so W-band will be included in that.
Yeah.
By next year.
Yeah. Any other questions?
Any other questions? So let's thank our speaker. Before we disperse for the break, we would like to felicitate our morning and afternoon speakers. I invite Dr. Subrata Kumar Das to kindly felicitate Dr. Roberto Femminini. Now I request Dr. Dupa Balding to the stage. Request her to kindly felicitate our next speaker, Dr. Jyothi Dutta. The tea break. We'll start with the last session for the day. Small announcement. Arun Kumar is called at the desk. Arun Kumar.
So, I'm back. Are you tired? So this is the last talk of the day. We will move to really practical but relevant application. Really what is Mole Antonelliana. So it's one of the oldest monuments in Turin. And you see something here. What is it? Mountains, no. Yes, mountain in Italy. We are dividing 20 regions with each one has an environment agency. And the weather service, hydrological service, avalanche service, all these operational services are located in this environmental agency. So as an agency, we belong to the government, and we face, for example, okay, the main center is in Torino. We are about 1,000 employees, and we face all environmental problems. So pollution, for example, environmental education, for example, or climate change. This is our office place. And this is northern, is a old map of northern Italy. Torino is here. In those are topics covered by ARPA. As environmental agency, okay, our department is a regional weather forecaster. It faces the natural hazard, but also face air quality, water quality. Then we also are in in charge about electromagnetic monitoring and pollution, ionized nuclear plants, but surrounding countries like Swiss and France have nuclear plants, and so we have a monitoring network, automatic network for early warning about radiation, nuclear risk, and then also environmental education and reporting. So we made several reports, even in about weather and climate. So there is a report about the climate of the past month, of the past year, and so on. Our office is focused on the top topics. What's interesting is that meteorological, hydrological, even seismic and avalanche, all these topics are covered by the same colleagues that are in our department. So we have in most of the other countries, hydrologists and the meteorologists are in different agencies. In Italy, this do not have. So our department is the Department for Natural and Anthropogenic Risk. We are part of the National Civil Protection. So our duty is we are responsible for monitoring atmospheric weather condition and also river status with a lot of hydrometers, discharge, for example, but also landslide. That is another huge topic in the Alps. And also we have to manage our meteorological, hydrological, and snow automatic network and manned networks that are located in Piedmont. And we produce several bulletins. Some of them are related to our topics. So if we consider disaster in our country, we see we come then since 18th century to the in Piedmont. What means disaster? It means, for example, landslide. Here you can see this landslide caused 4 or 5 deaths, and then floods, and this is another floods. And if we go back in time, and this is part also of the story of ARPA and of all the process. So the story in our department started in 1994. There was a huge flood. This is the amount of precipitation in 3 days. Look at the peak for 450 millimeters or for 500 millimeters. Oh, in that time we had all the rivers, all the main rivers flooded. But what is tough was that most of the peak discharge happens on Sunday, and on Sunday is holiday, so nobody take care about nothing. So we had this trouble, and so these events push us to create, to develop a model, to issue warning, and to make people aware about what's going on. Other stories. Here, so more rain, but in 2 days. To the Alps, you see there is a sea, and there is a sea here. So humid air can comes, or we talk about atmospheric river flow. Yeah, so there are some studies that demonstrate synergies, obviously, but no people dies. So that means that something changed. Also, infrastructure changes. This is the bridge over Alessandria that causes flooded in 1994. The new bridge, this is the new bridge, and you see that the new bridge was built properly because the other one was too low, and so the river was blocked by the bridge and then flooded into the town. The new bridge was make a good job, I would say. October 2000, for example, other damages, obviously, again, it works. And you can see the amount, even a huge amount, 650 millimeters yes. On such floods, we develop a process to issue one. And then collaborating with the National Civil Protection, this model was exported to all the rest of Italy. So as I mentioned, our organization is divided at a regional level. So here is Piemonte, our region, Lombardia, and so the other. This is a photo of the national law that states the new law about warning in Italy. And it states that each star is responsible for issue warning, each star. And then there is a center, the National Civil Protection, that coordinates everybody that make. If you go to several other countries for historical reason, you have a warning for severe weather condition, then you have a warning for flooding condition, then you have a warning, then you have emergency. So in Italy, given this new organization where meteorological landslide evaluation and hydrological river evaluation is all in the same office, we make a forecast of scenarios. So we do not issue a warning for heavy precipitation. We issue a warning for something that is going to happen and that we can imagine. What means that we can imagine? It means that I imagine that for the next 44 hours or 48 hours, I expect flooding, some landslide in part of the region, or heavy snowfall in the Alps, avalanches, and so on. Doesn't matter how much is the rain is forecast. You get rainfall, even a small amount of rainfall can cause damages. So this is our approach. Obviously, if you wish to make an evaluation of the next condition about risk, you have to start from monitoring and couple with forecast. But with forecast, weather forecast, but also hydrological forecast, and also landslide probability. So some models related to landslide chance, landslide occurrence chance. And then, so in our approach, green is everything is okay, or almost okay, because some isolated events, reverse thunderstorm can happen. But the color increase, change as the phenomena became more severe and became more diffuse. So when we saw the previous events, 1994, 2000, we see that large part of our region was interested by heavy rainfall and then by flood. So that's the meaning of red color. That's even were coded by red color. And then, given the red colors issued by our department, some action are taken by municipalities. For example, with the red colors, schools are closed. For example, some roads are closed because to the expectation of flooding by rivers. Can I go over? Yeah, it works. Yeah, which scenarios can we face? We face river floods, thunderstorm, snow accumulation, avalanches. But which kind of avalanches? Avalanches that interest the infrastructure or towns or roads, for example. And then landslide. But the warning is issued on the effect of the consequences of the rainfall over the territory. Yeah, there is you don't have to read this obviously, or even because it's in Italian. But I expect some landslide, so I expect a power supply interruption or destruction. I expect traffic jam. I expect people that stay in car because cannot move. So some unreachable places, then you need to evacuate people or to provide food, for example. So that's those are our scenarios. Thresholds. So the threshold is based on rate of time period. The rate of time period is an hydrological Cournot's rate of time period. Yeah, an hydrologist. Yeah. So the idea is that if you have longer enough time series of observation of maximum rainfall or discharge level, if you consider all this sample and you take only the upper tail, and you can fix, for example, a percentile, 99 percentile, it means that when your observation overcome these thresholds, even 99 percentile, it means that the chance of 100 years. So it's a measure of probability to 100 years rate of time. You need a longer time series. Otherwise, with the statistics that dominate this
measurement, it's practically very difficult.
We have a station. So we have stations from 80. So we have the weather station and automatic weather station that came from 1945, 46, 1945. So we have less than 100 years. Analyze statistics JEB, and then you can by statistics you can consider your sample given more than one weather station as a single point, and then you double. For example, you can double your sample. Then you fit with a gamma distribution, and then you 1,000 years
long.
There is a paper that I wrote estimating extreme values on hourly basis based on weather radar observation. So you have few years, but you can take the advantage of having a lot of observation.
Okay.
With the regionalized analysis, statistical analysis, you can consider, if you consider the decorrelation, spatial decorrelation, you can consider such measurement at certain distance uncorrelated. Then you can, if you are in a homogeneous climate, you can put all together and to make a some synthetic longer time series with some statistical method. Obviously, 1,000 or 500 years or even 200 years are not really reliable. The big assumption, there is a big assumption on this story. 100-year weather. Which is the big assumption? Stationarity. So in the climate change, something could work. Okay, so threshold 1 and 2 are related to rain gauges. One is 20 years for 1, 3, and 5 years for the other accumulation. So 2 and 5 are for the shortening intervals, and longer accumulation intervals are the thresholds. And then 20 years for 6, 12, and 24 hours lead to orange level of observed or expected if we forecast such rainfall. And these instructions are related to reverse discharge, and you see that okay, 2 years is a moderate flood, so only really some small parts of the river are flooding, close to the river are floodings. Meanwhile, for right on time greater than 20 years, we expect even some parts of vulnerable buildings, roads, and bridges are affected by this. And this is the reason why we issue a red alert. Also, we divided our small region. Kemote is 25,000 kilometers square. So it's very unrelevant respect to India. Yeah. But nevertheless, we divided this in 11 warning areas because those are homogeneous from several points of view. Obviously, the climate, but even the rivers and also the vulnerability, the risk. So in this way, we can focus on different topics. If you consider, for example, here we have the avalanche. This is the avalanche risk. So here we have the avalanche risk. Meanwhile, here there is flat plains. There is no avalanche risk. Okay. And also, nevertheless, there is even administrative and political issue because you can warn it. You know. So this is a forecast issued by meteorologists. So the meteorologist is our office takes the weather forecast and then they adjust the direct model output, giving, for example, in this case, for the next 12 hours, we're forecasted 110 millimeters or 100 millimeters and so on. And then there is one expert that evaluate this first guess and then decide about the corresponding color for each of these warning areas. And then, sorry, it's in Italian, but this is our forecast. Is our warning bulletin. So it means that here gives the warning level, and these are the reason for the warning level. I can read. This is flood, river discharge. This is a landslide. This is a severe thunderstorm. This is snow, and this is avalanche. So when you read this, for example, you can see that the trouble in this area is related to avalanche, to snow for the following day, and again avalanche. And these words describe what is expected. So we expect avalanche hitting roads in the valley, can cause some power supply interruption and so on. Yeah. And what's happened? Happened that given this scale of color, there are some action, as I told you. So this is automatic. So it means that municipality have to do something. For example, when you move from orange or red color, they automatically have to be in this condition, pre-alarm. What means pre-alarm? It means that they must be ready. And ready means that, for example, they set up an emergency room for monitoring what's going on. They set up tools, cars, for example, and all stuff needed to face the incoming emergency.
Suggest evacuation.
Do you?
Suggest evacuation.
Evacuation. Yeah, indeed, we are not responsible for evacuation because it's a matter of Ministry of of Security. But they call us asking. Yeah. So the the problem is that at the local, in the local emergency room, they understand that there could be an evacuation. Then they call us asking for example, detailed weather forecast or river forecast. It happens in Alessandria to me. Yeah, because the river is running downtown, so 10,000 people are interested by chance of flooding, and there is a barrier, and this barrier was so the forecast was 2 centimeters below the upper level, so the flooding. So in that case, they asked us, and the job was was good. So they didn't need to evacuate people, but obviously, yeah, happens. It may happen that they ask. And then I wish to, yeah, this symbol is CAP, CAP, is a standard common for issue warning. This is machine-to-machine protocol. So this is useful because if you use such protocol, all emergency people, civil protection, and fire brigades in Europe, and I suppose at least even in the US, are able to automatically switch some devices or fire a light or switch on a telephone. Yeah, from the meteorological point of view, you have seen our warning do not contain any information about the weather forecast because it's as I mentioned is a scenarios warning. Then we issue also warning bulletin related only to atmospheric or atmospheric phenomena. So heavy rainfall, severe thunderstorm, but this is not. This is needed to explain what's going on. This is useful also to include some relevant atmospheric phenomena like strong winds. We have. Do you have downslope wind in India? India also there is a downslope wind that is called the fan. The fan is a typical winter wind, winter or spring wind, and it can reach 150 kilometers per hour. So that can be dangerous for in some conditions. For example, if you have huge events in the open air. So this is only for this document is only related to wind to weather phenomena. Then I'll translate from you. So precipitation, thunderstorm, snow, hot or extreme hot or extreme cold, wind, fog. Do you have fog in Mumbai maybe? No. In Delhi, yeah. And then frozen, late frozen during March or April if we have late temperature below zero in the late on the early spring. This is dangerous for agriculture. Yeah, this is our monitoring. This is a federated ground network weather station. So it means that we operate this in this region, but we also share data with France, Swiss, and neighbor regions. So we operate a ground network of 400 rain-gauges. And it means that our rain-gauges density is 1 every 77 kilometers square. So it's quite dense. And but also you can see some triangles. Those are discharge or hydrometers. So we have a lot of them. The number is 100 and it's Britain actually. Yeah, this is only some years ago. Yeah, but it's water level. Yeah, 131. But also we manage, well, you know now, we manage operating also the radars, but not only considering our, oh, those are also other instruments. And this is a little bit of station, but we also operate a radio sounding, an automatic radio, atmospheric radio sounding. You can find the WMO GCOS system, and also this is breaking approach, and this is Monte and also now this instruments has been replaced by some LiDAR. Yeah, we have some vertical point LiDAR and scanning LiDAR for the CTF3. But also we are federated with other countries, and within Italy we are part of the radar network, Italian radar network, and we also share data with Swiss and even with France. This is the coverage of the radar coverage of our part of the region, and all obviously models. Then I will move faster because this is only I want to go because otherwise it makes late. So obviously we get NWP models to evaluate the weather forecast for the next days. We issue warnings up to plus 36 hours, and then each days we perform a briefing with the regional civil protection, providing the weather forecast for the next 3 days, and one per week we issue a briefing with the long-term forecast for the next 10 days. This is for planning. Yeah, because once there was a story. Once they call me and they say that we want to send people and trucks and whatever in another part of Italy for an exercise. And this happened the next week. Then I say, next week we will have a plan. Maybe it's not so safe to send the people in another part of Italy. Yeah, and they find a solution for the problem. Okay. Here I will go fast on the next slide because those are related to hydrology. But just to say that it's relevant to get also part of this, and is part of my idea that collaboration is the word, the necessary word, because only in this way you can understand the requirements of different radar data users. So this is our flood forecast system. It was developed by the Danish Institute. Is Mike 11. Is a tank hydrological model, and then consider that our basing. Well, this is main done for big rivers. Big rivers means river with a basin greater than 1,000 kilometers. So this is the everyday hydrological forecast, and yeah, and also there is a huge work because as told yesterday. Hydrological forecast is a matter of mass conservation. You get rain, this rain goes sometimes in some places, sometimes evaporated, sometimes infiltrated. So we have to move from river levels to discharge, so meter cube per second. So this is done by this conversion. Yeah. A law that converts river level to discharge in terms of meter cube per second. So this conversion is done by measuring, by going into the river section and to take some measurements and to get the law. Oh, I will skip this. I want to show you another. There is another models. So not only one hydrological, we have another category of model, fuse. This is a distributed model. So it's more similar to the model that you showed yesterday. And then, so this model is indeed a family of models. And this is a common technique. It's called ensemble. So you get several hydrogen, several forecasts, and then you can understand how reliability you have in the forecast. And then here you can see an example. So those are our thresholds. This is a meter cube per second is the discharge. Okay. Oh, this is the discharge of Po River just in the last point in Piemonte. So going further, you move in other region. So it means a basin of 27,000 kilometers square. And then this is the discharge, and this was the forecast issue on 2016. Yeah, the case I showed before. And then you can see that okay, you have different forecasts, and then you can evaluate how much confident are you in the hydrological forecast. Okay, this is the flood balleting. Here you can see what I mentioned. Sorry for the color. This is not color. It should be orange. Okay, so this is the river. This is the river, and when you get red, it means that almost the river is flooding. And then we issue a bulletin regarding the rivers. So there is a main document that issue a warning, and then other documents that describe the weather condition and river condition. Okay, then I skip. We use also the hydrological modeling for draft forecast. This is easy. It's easiest for other reasons, but it can be even dramatic. We got severe draft on 2022. So we very. Oh, there is a. I hope. I don't remember. Yeah, here you see a picture. Okay. We skip this. Oh, there is also another topic. If you deal with mountains and snow, you have to also to consider the snow water equivalent and change in temperature, because if you have rainfall and you have an sudden increase of temperature coming from the winter season, you have in the rivers you get the rainfall, the precipitation, but you have also the melting snow. This can increase suddenly the river levels. Warning. During an event, we make several notifications and we publish a lot of numbers that helps people to understand what's going on. And these are official documents, but by IT company. And in this tool, there is a list of people involved in civil protection with numbers, emails, phone numbers, emails, and then we issue automatic warnings based on ground measurements. If a river is overcoming a threshold, so there is an automatic warning spread by SMS or email and or email according to the people, and then you get warning. And the same happens for rain gauges. I show you what's happened for the rain gauges. If we have an overcoming threshold, then issue, for example, by this or this, all municipalities that are in within 15 kilometers close to this range are notified by this warning. And even us, as a main center, are notified.
Automatic warning
Yeah.
is not rain.
At the moment, there are other automatic warning they are, I would say, watch, not warning. Yeah. I would say watch, and I will arrive based on weather radar. But the most effective, you see an example. So this is based on rain gauge. Here you see there is a rain gauge. This is 15 kilometers, and all municipality. This is the municipality border. All these municipalities are notified about this severe condition.
So, like previous slide given, it's like 10 kilometers.
15.
15 kilometers.
Yeah, this is made according to the network density, to the rain gauge network density.
But with the radar, it is going to be much closer, or
rivers. The same happens for rivers, and here, this is and these are hydrometers. This is the rivers. This is the chance of flooding, and so when there is instruments that overpass the thresholds, again notification. Which municipality? All municipalities that are along the river. Yeah. Obviously, those are the most sensitive warning, because when a river is high, then something is going to happen or is yet happening. But we issue those are an example of notification. So this is by SMS on the mobile, and this is by email. Yeah, you get the place, the time, and the hour, and the current value, and all the thresholds, so you can easily understand what's going on. Yeah, the problem is that we set up this process because sometimes your forecast is not good. You do not expect that something happens, but it happens. So that's a reason why. Weather radar. You mentioned about this. It's raining. Yeah. So we did some watching on wait. I know it works. Okay. No. Yeah. Okay. We issue some warning, but this warning is issued to all citizens related to severe storm. Why this shift from so the previous model of warning was target to people involved in civil protection. The problem is that the time developing of thunderstorm is very fast, and you have time to issue a warning to a civilian that or police that makes something. So it's better to issue a warning for citizens, and this is based on the storm severity. I will define, and also storm tracking. Here you see an example of a severe storm that started. Here maybe you can see the time was 1:30 p.m. and then after 2 hours, this is Torino. So this thunderstorm was caused several damages by hailstorm and several damages to buildings due to the strong winds. And this is our forecast for the next hour. And it's made according to the speed, to the thunderstorm speed velocity, and then to the displacement and so on. So we made the app by phone. You can select your municipality you are interested in, and you get notified by this severe warning, severe thunderstorm warning. How we decided that a storm is severe? So for us, a severe storm, according to National Weather Service USA, a severe storm is characterized by strong wind, by hailstorm, maybe by tornadoes, and by high intensity, instantaneous intensity rainfall. So we try to modelize, to make a conceptual model of this, taking account several variables observable by weather radar. The first term is the wind density. So it's the VIL divided by the ecotop of the thunderstorm. And this number, try to normalize this value. This number is the threshold for large hail. So if your DV density is greater than 3.5, then large hail is expected. Large hail means hail with diameter more than 2 centimeters. This is related. This threshold is related to our algorithm to identify cells. The lowest threshold is 36 dBz, and then this is the normalization. This is obviously the average reflectivity of the storm is related to the intensity, the average intensity of rainfall in that storm. And this is probability of hail. Is another variable. This is not saying anything about the hail sites, but it's an indicator of chance of hailing. And this is also can be also problematic. And this is a factor related to the area. Consider since 2018, from 2018 to 2023, and then I consider percentile, different percentile to issue one. So, for example, the 50%, the 50 percentile low, if this variable is less than the 50 percentile from that climatology, we consider a weak thunderstorm. This is also a good correspondence. And with 95 percentile, we consider severe thunderstorm.
Yeah, so this 80 you got from where? 80 in the denominator.
What? Sorry?
In denominator.
Oh, 80. Yeah, sorry. This is 80 because typically we don't. Yeah, it's very high value in reflectivity. Yeah, that's some. No, I look at for this data. I look at the statistics over this period. So the main idea is to make each factor weighting almost the same, because otherwise one factor is more relevant than the other. And I look at this time series for all the cells, and then I found that sometimes we measure 80.
And this area is like strong area, like continuous cell. This area.
Yeah, this area is the elements that cover the 98% of the area of the storm. So the area of the storm is identified beam by beam, cell by cell, but then is simplified as an ellipse covering the 98% of the cell.
Yes, so in one storm, you will have multiple this kind of the thing. So you do for each every cell like this.
Yeah. I will show you another.
Yeah. Just wondering that false red alarm of this.
Oh, we can discuss because I had it. I had it. Oh, this is an example. Oh, I go back here. So this thunderstorm starts at midday, and we track for 4.5 hours. So this was really a long-lasting thunderstorm. And according to this, we had hail accumulation here, several fire brigades intervention here, and so on. And if we see, we can see this is interesting. So you mentioned several cells. I track these cells and report the cells parameters on this graph. So this is the severity for this, and then I get this is VIL, and this is the mean reflectivity. This is the maximum reflectivity. This is the cloud top from satellite, and so on. This is interesting because you get getting good data set from several years. You can study some climatology. You can study thunderstorm climatology. You will see, for example, that there are some hotspots in the place where thunderstorm born. You can find some weather condition where thunderstorm lasts for more than 1 hour, and also you can find some weather condition where thunderstorm travels faster or slower. Obviously, the slower thunderstorms are the most dangerous. Yeah. And I made a correlation between fire brigade intervention in the city for the past summer and severity. There is a weak correlation, obviously. Yeah, there are much more work to do to understand, because when you have a fire brigade intervention guy, you are really evaluating the impact, but the impact is very different from part to part. And also there are some social anthropic aspect. For example, in some I would say remote places, but remote in India is a completely different meaning, I suppose. When you see some remote place, people do not call fire brigades. They try to solve the problem by themselves, for example. So there are also some question about this. About false alarm, 84%. This is the false alarm derived from this evaluation made by severity and fire brigades intervention. But this is an ongoing study, because now I try to get more information about the places and what's going on. But obviously with thunderstorm you get a lot.
Can you go a couple of slides back where you had a forecast? I guess there was a forecast code. Yes. So I can see that from the initial, close to the storm initiation place, you have a forecast cone ahead. So how do you make this forecast cone for the next couple of hours or something? Is it using some regional model, or is it something based on real-time monitoring radar?
It's only based on weather radar, because there is no time. So it's based on thunderstorm displacement and historical, and then so this is the uncertainty. So the wideness of the cone is derived from historical data. So meanwhile, the displacement is derived from the past displacement of the storm. So, for example, if the storm is moving 60 kilometers per hour, I suppose that in the next hour it will take 60 kilometers. This is called persistence, something similar. So I suppose that the storm may be the same.
Yeah, but the storm can die even before that particular place, right? Like it may not go even to that end of that cone. So, like, how do you see the possibilities of a storm, like getting diminished even before that?
Yeah, this is a good point. Yeah, obviously this works. Yeah, when you have few storms and the long-lasting storms, when you have yeah, new cell and new developing storm, yeah, it fails. I agree.
Okay, thank you.
Oh, I want to mention another experience. Events, so social, special events. So in Italy in 2017, there was an artist in Europe called Cristo. He's an Hungarian artist. He developed the floating piers. So I make such a structure over the lake without any barrier, without nothing. Okay. So he said that it was a really good idea. We said it's a very good idea if there is sun. If there is a sunny day, even with some trouble with skiing, because over the lake was people had some trouble. But you can easily understand that when you are, oh, this is a true picture, it's not generated by artificial intelligence. So this happens. So you can imagine what's happened if a serious thunderstorm hit this place. You have people, oh, the farthest distance from the river, from the coast, sorry. River means coast. From the coastline, the farthest distance was 1.5 kilometers. So you imagine some kids 1.5 kilometers over these piers, and the thunderstorm is coming. It's not really safe. So even if you have strong winds, for example, even waves can arise in this lake due to the shallow water equation. You can even you can even get 1 or 2 meter waves high. So obviously we are focusing on a small area with a lot of people. So our goals, our aim were well defined: people's safety. So what we were looking for thunderstorm and thunderstorm approaching to this installation to make people get to the coastline. So we installed the X-band radar in this place, and I want to show you. Okay, this is the place. The place where the previous photo was taken was here, and this is the radar place, and this is the installation of our X-band radar. So during this experience, so no protective barrier, as I mentioned. This is where the dimension of the piers, and then we are in the complex orography. We are in the Alps, and with max expected gust was 55 kilometers per hour, and then we put the X-band radar here 5 kilometers far from the place. So for these events, we define a specific scan. In this case, even 1 minute is relevant. So we don't need volume scan. Well, we need lower elevation scan, but faster. So it means one elevation or couple of elevation, but 1 minute repetition time. And here you see integration between our target area, our target area and weather radars. This picture comes from C-band operational weather radar. And this circle are 10 kilometer distance. And obviously, we define with the organizer a protocol. So when we see a thunderstorm far from 80 kilometer or 60 kilometer far from the target area, you should start to make prevention. You should limit the access to this place because it's becoming unsafe. And this is the X band. Look at, there is something more. If you look at here, so this is a developing cell that was not seen by the C-band radar because it was shallow and the operational weather radar observed only upper levels, 3-4 kilometers. Pontelema, yes. So that's the benefit of having X-band radar close to the target area because you can add some information, especially at the lowest level. So recalling this morning when somebody says, oh, it would be nice to have a radar in the top of the hill. Okay, you gain huge visibility, but you lost something that is happening at the lower level. So we should find a compromise and according to which are our goals. In the case of ACQPI in California, we want to observe orographic precipitation. So we need observation as close as possible to the ground. So that's and okay. The cross this cross are lightnings, and then okay. Only I want to to show you. Yeah, this were the temperature. Okay. Like springs for you, or I like winter for you. Okay, and finally, we make an automatic balloting based on all this warning system that those are public, published on the website to state the current condition for each municipalities. So this is a picture, a sort of picture giving the current status. So the current status means that if we have yellow, this means this is the current status during the last time, and this is the status during the last 24 hours. So it means that in this place there were some issue related to heavy precipitation. Yeah, this was a balloting issue during a more widespread events in. So, which is our schedule? So we don't stay at the office. We don't cover as office 24 hours, but we cover from 8 to 18, 12 hours. But as the morning increase, even our coverage increase. And when we have a red alert, it means that we have to stay in the office monitoring and issue warning and answer to the question, how many people to evacuate and so on. How many people works? So 5 room manager, 1 is mine, and 10 meteorologists, 5 hydrologists, 7 avalanche experts, 9 technicians, and 9 geologists. So this is a number, full number, and this is the daily schedule for each one. So we have a couple of meteorologists each day, 1 room manager each day, 1 hydrologist, and so on. Okay. I think it's some same time it's on. So thank you, but it's time for questions.
Showed like accessibility index kind of the thing. So there you still use only the power measurement, reflectivity, not any colorimetric measurement.
So colorimetric measurements are in the process. Yeah, because we get for clutter suppression, for particle AD, so those are in the process. And Yeah, I believe that you get with polarimetry, you get, well, this is an ongoing work. Yeah, because the next step will be include QPE from weather radar in the automatic warning. The next step. Okay, but we are still working on that. And in that case, in the QPE accumulation, there will be more, there will be obviously polarimetry. But polarimetry is in the cluster suppression, is the quality signal and so on. So that's more evident.
So this will that will be used as the first that information. We will do the quality check, and after that,
It takes after the end of the scan, it takes 2 minutes to issue one. This is another. Now, when you talk about warnings, you have to think about the latency time because you want everything as fast as possible. So you can do. If we go back to the model, it takes hours to. It's obviously is needed, but it cannot cover 1 hour ahead.
so any numerical like Cosmos model you are using, right? Cosmo something you are sure.
Okay, so we are using limited area models, and now we are migrating to a new model that is ICON, is the new European model for limited area. So there is a global version of ICON, and there is a limited area model over Italy of this model up to plus 72. And we make also some rapid update cycle with the icons. And Renzo is an expert in nowcasting. He made 1 hour forecast with starting from weather radar blended with NWP. So if you want to move to 3 hours, for example, only the weather radar has demonstrated that it has a poor skill. Only observation. But if you blend with NWB, you can gain something. This is another way of investigation for us to include in this system.
Blending how much improvement?
Up to 3 hours. And the methods is to blend, so to reduce the impact of observation information as the time increase and increase the value of NWP forecast. So this gives continuity to the nowcasting forecast, and then you get all the information.
Thanks for next. You were mentioning about the floating PS deployment. How often you get such requirements from?
No, hopefully not often. But I'm thinking about huge open air events. In Europe, music concert, for example. So there are some issue about these events because you have 5,000 people in the same place, small places, and sometimes thunderstorm can. Yeah.
So do you have some mobile radars for such occasions?
Oh, indeed, we use the mobile radar in two main events. One was Expo 2015, and the other was the floating PS 2017. In Expo, there were 200,000 people in the open air with some infrastructure. So this Expo are something that are not really concrete, are something I would say fake, because they are for the show. So, but these parts of buildings are very weak in respect to strong winds, hailstorm, or thunderstorm. So we install the radar and we issue warning, to the organizer to make people safer.
One more question. You were showing the thunderstorm tracking. Is it similar to NCAR's data?
Yes, it's similar to data. Yes, it's indeed there. I mean, it's another approach. You can make an outcasting basing on the fields, or you can make sometimes, especially with thunderstorm, sometimes the object-based forecast is better. So you have to mix and consider both of them. Yes, there is.
Everything started with the scenario analysis, but it happens very often that with the yellow code, so it's a relaxed energy. So something that can happen, but there is no real status. And something happens, for example, flash flood, some intensifications of a precipitation in some places. What happens?
If I go back, what I think. This is the ratio with the yellow. So the problem is that when you consider a thunderstorm, even severe, is really a local problem. Local problem means that 100 kilometers per basins or base or even town. But so in our model of warning, the efforts to face the risk increase with the color. So if you move from yellow to orange, for example, it means that some people, a lot of people have to work, and it means that a lot of action have to be taken. And you can imagine red color. So, but to face what? So the problem is that if you consider a single thunderstorm that hit Prato, it can be also dangerous, or it can cause several damages, but it's only related to it. So it means this axis. So it's maybe it's strong, it's quite strong, but it's localized. So for us, it's yellow. That's the meaning. When you move to these parts of the plot, it means that a lot of people is involved, a lot of people is working even during the night. So that's
but when you have a flash flood, often then is if you have a flash flood that is localized, this is severe.
Yes,
because,
but it's localized.
Yes, but you turn from yellow to orange somehow.
Yeah,
That's something.
it can happen. Yeah, obviously. Yeah, but the case of orange was I remember last spring. Orange was in Piedmont last June, 29th of June. You got severe. Yeah, obviously, if you expect flash floods, obviously you should issue an orange. But if you expect a severe hailstorm on a city, it's yellow for us because there is nothing to. So you must be prepared, and also the colors depends on what's going on. You know, in Italy we have the Pope. If the Pope makes an event, it means 1 million of people on open air, and you can think about what's happening if you have 1 million of people hit by a storm. So this is different from an ordinary storm. So this can lead to a different color.
Is it due to your resolution like 15 kilometers? Because your localized one pixel is like 15 kilometers, so that's why it is going in the orange.
No, it's related to small parts of the warning area. So if we expect a thunderstorm that can damage even one city, then you issue a yellow. The big problem with thunderstorm is that when you issue a forecast, you don't know exactly where it's happening. That's the big problem. So you have to find a compromise between making a lot of people working and making people reading.
So that's like a compromise situation to give like orange. So.
Yeah, that's the problem. And that's also the problem for early warning. So not the problem, the advantage of early warning, because you can identify parts of the region that will be eaten in the next 1 hour or 2 hours, and then you can concentrate your attention on that areas and hope that local people takes the proper actions to react.
The administrator has to understand those things. Scientists will understand, but for them is they need to deal with the public picture.
Yeah. My question is regarding to the storm tracking. Like here also in India, we are like related to this lightning rain also. We are giving that kind of thing. The issue is like sometimes the storm are moving in particular direction. There the uncertainty cone or maybe the uncertainty deposit will work. But some thunderstorm is expanding for a particular region. So in that case, how you are giving the alert, or there may be the multiple uncertainty cone or something like that?
Yeah, in part it's taken account in part it's taken account by the cone. If I go, where is it? No, yeah. Yeah, part of the process is taken into account by this. Yeah, it's very, if you consider the true track of the thunderstorm and the warning, you see, yeah, it's related to false alarm before. No? So you issue a warning for more municipality than expected because due to the uncertainty in the storm direction of storm evolution. Where this warning phase for sudden developing thunderstorm in a place, because there is no tracking, there is no thunderstorm, and within 20 minutes you get rainfall. But these are typically not so severe. So, but it happens. For example, in Torino, I remember there was the sun after 20 minutes, given the hill, we got a thunderstorm from nothing. And then the tracking fails, obviously, because there was nothing to track. And when this way is most powerful, when you have a long-lasting, especially isolated storm, like the storm like this. And also there is another issue with the storm tracking. Sometimes this is a part of the story. Sometimes you have damages.
So I wanted, so this is something.
Okay, once a day with the weather forecast or twice. Okay, once a day with the weather forecast or twice with weather forecast, but every hour and put inside the weather radar observation, for example, or an nowcasting.
So the administrators are able to understand because we give too much forecast, they get confused.
Yeah, but what's happening is that when we issue
from the numerical weather prediction model or radar.
This comes from
the numerical weather prediction model or radar.
This comes from numerical weather prediction. Okay, but then you have to monitor and make an forecasting of river discharge evolution, because sometimes they ask you, okay, when the maximum peak is expected, and then you can update this information during the events. So this is needed, really needed. And also the maximum peak discharge value is a number that is needed because it corresponds to level and then it corresponds to scenarios. Evacuate people or not.
The other question I wanted to ask is, given these forecasts for any reservoir operation,
Sorry, for
a reservoir operation.
Yes, obviously, yes. There are several dams in the Alps, and all operate given the day forecast and the morning, they start to discharge. And also, yeah, the problem is that in some critical condition, they communicate to us the discharge values, and we need to make a forecast on that river, where some parts of the discharge is natural and some parts comes from the dam discharge. So that's
we are also dealing with the same situation for Chennai.
Yeah.
So we are also trying to use the expand radar which is being installed and try to do the visitor approach. So since the lead time is less than 6 hours. So if we are able to get the rainfall from the radar, we will be able to operate it accordingly.
Yeah.
Thank you.
Yeah. This particular case, you were saying about a storm that you have a particular direction of propagation. So my question is about some kind of a surprise storm or a convective cell that can pop out in a region away from this. Maybe like there's a cold pool and the gravity wave, like new developing storms, which is really away from the storm's main propagation direction.
No, but yeah, but it's a good point because given the Alps, so the typical meteorological condition for cold pool. Okay. So what's happened? Typically happens that the cold air comes here, those are the Alps, and then you have cold air flowing through the valley, and then they set up a convection just in the at the exit of the valleys. So it's a product on in Meteosat called RDT, Rapid Development Thunderstorm, is a satellite-based product. So we track and tall thunderstorm, so minus 60 degrees, for example, tropopause thunderstorm. And then in our experience, when this such thunderstorm touch the Alps, they push cold air into the valley, and then the severe thunderstorm, you must stay in front of your PC to look what's going on.
Thank you.
Hello, hi. Thank you for the wonderful talk. I had a question regarding the severity function. So I was wondering if you can throw some light on how exactly the probability of hail is estimated. Is it purely radar based, or you also include things like convective instability or weather?
Radar meteorologist, and it is based on the principle that you may find high reflectivity aloft, and this is a signature for having a chance of hail.
Any other questions? Let's thank our speaker, Dr. Gupta. So we have a few announcements for tomorrow. The buses for the visit will be leaving from the hostel itself, Prithvi Hall of Residence. Please assemble by after the site visit. So be there at the site visit. So be there at 7. Next, if you have not submitted the TA forms yet, if somebody has not submitted the TA forms yet, please submit them to the security main gate. And lastly, for the HOD recommendations, those who have not submitted the original recommendations, please post them as you have been informed via email as well. Thank you. That is it. We discuss for the day. Thank you.